Very cool. Okay, so I guess we'll start now. Yeah, it is my great pleasure to introduce Michael Sperber. He will be doing this session for the beginners track. Michael, I would say, is one of the most competent people to teach programming and function, in my view, functional programming and programming in general. He has had a long history of this. Maybe some of you know his book, Schreib dein Programm, yeah, which is used by many universities to teach programming. The book that I used to learn programming is sort of like it's in the same tradition as SCIP, Structure and Interpretation of Programming Language. Would you agree with this?
No.
No? Okay, good. I take that back. Cool. Okay. Thank you very much, Michael.
I'll answer questions about that maybe tomorrow.
Yeah, cool. Thank you very much, Michael, for being here. Take it.
So even my German language friends call me Mike.
Okay.
And you do too.
Yes, I thought I'd use your formal name, but yeah, thank you, Mike.
So, welcome. So I'll say a few more introductory things, so I'm used to sort of teaching very large classes that are very homogeneous and very small classes that are very heterogeneous, and you're kind of in the middle. So we're going to have to figure things out. So presumably we're here at ZuriHac, so we're all here to learn Haskell. So first question is, I see almost everybody's got laptops set up. Who does not have a working Haskell installation yet? Okay, so then I would invite everybody to go to this page here. So because it might take a while, we're going to get that. Well, I'd like to say we'd like to get that out of the way, but Haskell is sometimes a little tricky to install. And that has a README file that has instructions for installing Haskell, either sort of from scratch, using a tool called GHCup, or usually at ZuriHac there's a lot of people here who have Nix, and there's also working Nix set up in that repository that you can check out. Let me go through that a little bit. As I said, I'll make introductory remarks, because it might take a while. So here's the repository. It tells you, for most of you, I think, what it will mean. If you don't know what Nix is, then the way to do it is to do it using GHCup. And that has shell commands that you can type in to get you started, and those will take a little while anyway. Once you've done that, you should make sure that you answer this question. At some point, it's going to ask you, do you want to install Haskell Language Server? And if it asks you that, HLS, then you should answer, yes, I absolutely do want to do this. And then once all of that is done, you should type in those two commands, and that will also take a little while. So that just installs sort of the GHC compiling environment and compilation tooling. You'll also need something to write your programs with. And if you don't have like a working super cool Emacs or Vim setup, of course that also works, I recommend you just install Visual Studio Code. And then there's instructions, on how to start this. There's instructions on how to start this. And of course, in Visual Studio Code, you should install the Haskell extension that's there. What's kind of important in this in whatever we're going to do, if there's any sort of problem, so I'm going to let you start this process. It's going to take a little while. If there are any problems, please let me know. This will mean that within the first half hour, I think we'll have quite a few interruptions, right? That just goes with the territory so that we get everybody set up. You might also check if you have somebody already knowledgeable or has Haskell installed right and sitting next to you. You might also ask that person. So we're not doing something super special. So if you have an existing Haskell installation that you got via some other methods, that is also likely to work. Okay, so far? So I'd like to ask you to get that started. And if there are any problems along the way, please, raise your hand, let me know. This goes for everything in this class, sort of. We're going to do sort of a lot of programming together. I'm going to do a little bit here. We might do some exercises. We'll try to figure it out. But if anything doesn't work for you, or if you've got the slightest question as to what is this thing doing, why is that doing the thing that it's doing, why is this language the way it is, all questions. I mean, somebody asked, is there like a minimum requirement or a maximum requirement? No, there isn't. But in order for us to get this thing going, it needs your cooperation and it needs you to ask questions and interrupt frequently, even though it might mean that sometimes the others have to be a little bit patient. But we'll try to make the most out of those 3 hours. Okay? So far, so good. Let me say a little bit about who I am, and so that you have an idea what kind of questions you can ask me. So, my name is Mike Sperber. I've been programming since 1983. Who was alive in 1983 in this room? Okay, well, at least a few people there. Who's been programming since 1980? Probably. I've been thinking about teaching for a long time. So my first book came out in 1986. I got my PhD on stage lighting using functional programming. And as Farhat mentioned, I've designed for a long time in my career. I was working on designing an introductory programming course that is still in use at the University of Tübingen and occasionally at a few other universities. But since 2004, so that's over 20 years now, I've been doing practical software development, and I've been CEO of a company called Active Group since 2014. And Active Group is a consultancy that does all kinds of software projects using functional programming, not just Haskell, but also in Haskell. But also using other functional languages such as OCaml or Erlang or Scala or Clojure. So if you're interested in sort of comparisons to those things, then I'm probably can say a little bit about that. I also think a lot about software architecture, which is about what happens to software when it goes on for a long time and it grows very large. Then maybe there's a few things you need to do differently from the 5-line Haskell programs that you find in most books. So I can also talk about that. We also teach classes in that if anybody's interested after the fact. And if you're interested, we also run a blog on functional programming. And I mentioned this morning already that we're running a developer conference, Bob, usually in March. Date for 2027 hasn't been set yet. But it's definitely going to happen in probably around March in Berlin, which also has a lot of people sort of that do functional programming or do other cool stuff in programming. Fun place to hang out, I think, Johnny Bob. So any questions? So this is kind of, so maybe what you get from this, right? So I've been doing functional programming for most of my professional life. That is, depending on how you count, at least 25 years. My knowledge is probably more wide than it is deep. So if somebody goes and says, some arcane corner of the Haskell programming language that just got introduced by something that somebody hacked together who's here at ZuriHac last year, I might have to pass that question on to other people who are at ZuriHac. But we'll find out. Okay, so far? Okay, so the installation of Haskell is ongoing. As I said, let me know if there's any snags along the way. So let me backtrack a little bit. So who's not had any exposure to functional programming at all? Couple people? Okay, good. Who's had no exposure to Haskell? Just so everybody in the room knows. So about half. Okay, some people have had some exposure. So that you all know what kind of bridges we have to build in this room. It's perfectly okay if you think if we're going down some route that you think is boring, but that seems interesting to somebody else. I mean, you can always interrupt me and try to get me on a more constructive footing. But if we're doing something that you think you've heard before, that's very possible. If you've had some Haskell exposure, then just leave the room. Do something else for a while. If you're interested, come back or put your head through the door and see if we're doing something interesting later. Nobody here will hold that against you, right? So it's kind of, ideally nobody's going to get too bored. It's not going to get bored for too long in this room. So if you feel like you've been bored for 5 minutes, then it might be an opportunity to take a break. Do remind me if and when we need to take a break would also be something. I'll try to do that myself, but I should say, sort of as a teacher, teachers want to teach. They don't want to take breaks. Does that apply to somebody else in this room? No. Okay. So I might miss that opportunity. Okay, so we'll see how that goes. Okay. All right. So you've noticed some of you have had some exposure to Haskell. A lot of you have had no exposure to Haskell. Some of you have had no exposure. There's been a few people who have had no exposure to functional programming. But you've been programming before in your life? What have you been programming in?
Java.
Okay.
C++.
Java and C++. Okay, you too?
Java and TypeScript.
Java and TypeScript. There was a few other people. C and C++. Okay. Okay, so we'll try to relate, if at all possible. So how do we do this? So maybe to continue, so you should have a working Haskell setup. I mean, it does make sense to check out that repository, but you don't really have to because we're not going to do much sort of, we probably won't be doing too much sort of non-standard stuff. If you're doing sort of the default route that is described in the README for installing Haskell, then it tells you to open a file called intro.hs that only has that single line in it. What's really important is that if you mess that file up, right? So if I delete, for example, the E that really needs to be there, then it needs to look like this. And by that I mean you can see that the where has turned red. That will pretty much always happen if you've got the Haskell extension installed. But also that you get this red squiggle underneath, right? So that is the important bit. If you've got that, then your Haskell tooling works. But a lot of things happen to that point and that can go wrong. So if you don't see this by the end of your Haskell sort of installation setup process, then let me know, and then we'll maybe group a few people together and see that we can resolve those issues that are there. All right.
If I may make a public service announcement, if everyone's downloading on EduRoam, the ZuriHac Wi-Fi is a lot faster than EduRoam.
Okay. Good to know. Okay. So question is, who is on EduRoam in this room? Okay, a few people. Okay, so built in. But you're doing okay so far? Things are progressing? Huh? Successfully downloaded. Okay. Do you know what the next steps? Can you infer them from the README? Or?
I think I've finished the download.
Okay. Excellent. Yeah, there. Yeah, that's exactly what it should look like. Great. And if you have a working Haskell setup and you're sitting next to somebody who's getting it set up, of course, it's much appreciated if you can help with that, right? All right. So those who know, I mean, everybody except for those 3 or 4 people, what is functional programming? So this is how teaching works, is I also get to ask questions, right? What is functional programming? What is the difference? Yeah, there's this funky thing. And so it used to be the case in the 80s, right? If you read FAQs on functional programming that would explain the term, those would say, well, it's called functional programming because functions are first-class objects, right? And this was sort of the original distinguishing characteristics in the 80s and 90s when really functional languages were the only languages in which functions were objects. Unfortunately, or fortunately, I don't know, right? In Python, functions are objects. In C++, functions are objects. In Java, functions are objects. So that's no longer something that we can use to distinguish functional programming from sort of non-functional programming. Yeah? What do you? Isn't that a immutable state? Yeah.
I mean, you always have some state, but in the sense that you as a programmer can't mutate inside of a closure.
Yeah.
And only have the state as an object or data that gets passed through functions.
Okay. So the point there was, first of all, the operative word is immutable, right? And so if you've been programming in Python or C++ or Java, sort of what happens all the time is that you have some sort of assignment statement, right? That it says, something like, x equals 5 or x dot a equals 5 or something like that, which will change an object in place, right? And we don't do that in functional programming, so that's a fair definition, right? I'd like to propose a different one, I think, that is more rooted in culture as it is in sort of technicalities, which is that in functional programming, it is all about data, right? And so recently, for example, the Java people have introduced some extensions into their language, which really duplicate stuff in functional programming, but they've described it as data-oriented programming, right? And what is the difference between data and objects is, well, data, definitely today, data is going to be immutable. So we'll need to figure out what that means. Okay. So before we begin, are there any sort of topics around Haskell or around functional programming that you've heard that you're specifically interested in that you would like us to cover? Like, I don't know, lazy evaluation. No, yeah, something, yeah. Huh? Theorem proving. Okay, I'm not sure we'll go. Oh, okay, so we'll see. So I'm just going to. Yeah, no. So theorem proving. Anything else? Nobody's interested in. Nobody's going to say the M word. Yeah? Applicative functors. Okay. Okay. Anything else? If you've never heard of that, don't worry about it. Right? Maybe we'll get to it. We'll
Parallelization by the compiler. I don't know if this is for now.
It doesn't. No, it doesn't do that. Okay. That really, I think, is out of scope for what we're going to do today. Okay. Anything?
Writing like programs that actually do stuff, right? Because
Programs that do stuff. Okay.
Database,
Yeah.
talk over networks, stuff like that.
If you're wondering, like, how can you write programs that don't do stuff, right? It's like, this is originally, in fact, the original version of Haskell didn't, so Simon would always say, well, the first versions of Haskell, all they would ever do is get your computer hot, right? So if that's your definition of do stuff, then that's easy, but everything else is indeed different, at least,
I would
right?
be clarified by like, do stuff in the real world, right? Not just, I think theorem proving is an interesting area of programming.
Yeah.
But what I do for a living is needs to like go to database, to talk to file systems, stuff like that.
Yes. Okay. Try to do that. It's going to be a little tight, though. So we'll find out. Okay. Good. Anything else?
Yes, like data modeling in the sense of
Yeah.
like making impossible, like only making impossible.
Okay. Data modeling. And you've maybe seen the Jane Street slide had a famous quote by their CTO, by Ron Minsky, which said, I think that's what you're alluding to, is make illegal states unrepresentable, right? Okay. So, and if you sort of follow my reasoning that functional programming is programming with data, right? I mean, you could also say make illegal data unrepresentable, right? That is the same thing. Back there?
I read that Haskell is purely functional.
Yeah.
I'm curious what makes other functional languages not purely functional.
Yes. Okay. Good. Yeah, that we can do. And?
I'd like to have a look at quick check if that's possible.
Okay.
I lack experience in a language where property-based testing works well.
Yeah. Okay.
Systems, I've heard the term a lot, but not sure what it actually means.
Okay. Okay, that's a tall order. So we're going to have to move fast if we want to cover a lot of this stuff. Okay. So the way, I'm sorry, I need to set something up. More?
Just a setup question. If you're using the Nix setup, when this code asks whether to use the path or GHCup? Which should I choose?
The path. Yeah.
Thanks.
Yeah, good question. Yeah, okay. So anyway, so mode of operation is going to be like this. So I'm going to be typing stuff. Ideally, you'd also be typing stuff, right? And if only as sort of a means to kind of pace me and tell me, Mike, you're typing faster than I can type. We'll find out. What happens is when I save this file, for example, right, is it'll automatically get pushed to that GitHub repo that you saw in the beginning, right? And so what you can do is you can just open a browser page on that GitHub repo and on that file, and if you're ever unclear on or if you don't want to type what I typed, right, you can just refresh in the browser and copy paste it from there. Okay, that's all right. Okay so far? Good. Then, so, and the way, I mean, because, so a lot of this stuff is, data modeling is going to be front and center of everything that we do here. We'll try to talk about all of these things. I'll try to, as I said, right, teachers want to teach, right? So I will try to cover quite a bit of material, but please, 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 let me know when anything I do is too fast or unclear, or if you've got any question whatsoever. And it doesn't just have to be a question, what are you doing right now, Mike? But it could also be, why are you doing what you're doing, Mike? Right? And what is this, maybe get, this functional programming. It makes no sense to me. Why should I do that? We can discuss all of those questions here. Okay? But I need to rely on you to tell me. I'm sometimes going to ask you, and I'm going to ask you to kind of look me in the eye and give me feedback on that I'm still doing something that you're all understanding. And please go, if that does not work out, right? If things don't compute in any way. All right, okay? So we'll try to do things fast, and then, there's enough people here who can sort of, if anything is sort of needs clarifying later, who can help with that. But as we're going along, make sure that we're, that everything that I do is sort of semi-understandable. So I'm here in the middle, or not in the middle. I've just started a Haskell module, so that's sort of the larger unit in which our Haskell program is organized into modules, and within a module, well, I can do whatever I want. And in a Haskell module, what it will usually contain will contain something, I'm going to call that an equation. Looks like this, right? You folks in the back, is the font big enough? Can you all read what's there, or should I make it bigger?
Make it like one step bigger.
Yeah, my pleasure. Let's make it 2 steps bigger, right? If it doesn't fit on there, then it's probably too much anyway, right? Okay, so I can put an equation there. You can also see that Visual Studio suggests to me that I put something here that's called a type signature declaration that just says that X has that type integer here. And when I click on it, it gets to be part of the program. So far, so good, right? And of course, we can also do something like Y equals X plus 5. So we can refer to Y and X. And if you want to try something out, then there's 2 ways of doing that. Depending, if you've got Visual Studio set up in this way, you can do a magic. So first of all, here's a comment. So it starts, so if I make 2 minuses at the beginning of a line and a space, I can make a comment right there. And there's a magic comment I can make by doing the 2 minuses followed by a space and 3 pointy closed bracket, greater than signs, right? And I could do something like, well, what is Y? What is that? And I can push that evaluate button. And if I wait a little bit, it will tell me, oh, Y is 15. Okay, that's very simple. Okay, so far? Good. Okay. Now, don't want to bore you with too many details. I said it is about data. So in functional programming, everything is data. And functions are data and all of that stuff. So that's maybe we should call it data programming or something in order to distinguish it. So in Haskell, when you are thinking about data and you do data modeling, you tend to declare new data types, and you do that with a construct called data. Okay. So and what we want to do is we want to do something very simple. Imagine, just going to comment that out for a moment. Imagine you've got like a pet in your house, or different kinds of pets, right? And you've got what are pets, right? Might be a dog, might be a cat, might be us. Does anybody have a snake as a pet? This has happened to me twice. Okay, then we need, we'll see why I need to know. Okay, so now if you look at this, this is kind of a description of data, right? A pet can be, could be a dog, could be a cat, could be a snake. Now we all think we know what this means because we know what all of those words mean that are here, right? But imagine, you're coming, you're a Klingon or something. You don't know what these words are. So you don't really know what kind of relationship they're in. And one way to describe that relationship would be to say, well, the pet is a dog or a cat or a snake, okay? And if you're not sure, you can just try that out, right? Try out the wording, try it out on your friends, see if that makes any sense, right? So it's probably not a pet is a dog and a cat, right? But it's a dog or a cat or a snake. Or you could also characterize this by a pet is one of the following, okay? So this is the way that I recommend data modeling starts with what I call a data definition, is you just, you talk to the domain experts in your domain and ask them, can you describe the things that are there, right? The things that you're dealing with, what are they? Is it this, is it that? And then you can see if you can put a word like or in between and see what happens, okay? So when you see that, so that is one of the, so when you see this thing, then really what you're looking at is you're looking at something, I think I'm going to call that a case analysis here, right? There's different cases, right? One case is dog, one case is cat, one case is snake. And you can, one of the things you can always do is you can, when you're learning a new language, you can look at data definitions and you can ask, how can I translate a data definition into code in my programming language? So in this case, we can write a piece of code that looks like this. So we're going to define a new data type. Conveniently, it's going to be called the same as in the data definition. We're going to call it pet. And then I'm going to write dog. And then I'm going to write cat. And then I'm going to write snake, okay? And you can, you already heard me say or, so the vertical bar here means or, just as it did in Simon's talk this morning. I guess that's common notation. And hopefully you can all see that this data type definition, right, corresponds to the data definition that we see up there, and it corresponds 1-to-1. Okay? Does that make sense? And this should basically always be the case. And I can tell you one of the major sources of grief I can see in data modeling is people have a data definition up there and then they think they should do something funky when they write the code. Don't do that. Make the code correspond to the data definition. All right? So far, so good? Yeah?
Does this bar only mean the or?
Yeah. Okay. Yeah. So in this context means the or. Not sure it means anything in other contexts in Haskell. Okay, does that make sense? Now, important, Haskell is an indentation-sensitive language. And the idea is this: if you have a construct that goes across, that spans multiple lines, like this one, which spans 4 lines, then all the lines after the first one need to be indented with respect to the first one. Okay? So let's see how that plays out. So, you could go and put all of this in one line, for example. That would not be a problem at all, right? But if you decide I'm going to distribute that across several, you can already see if I do this, something is wrong, right? There's a red squiggle here, and the reason why there's a red squiggle is because this vertical bar here is in the same column as the D, right? You can see that. And the squiggle, well, it's not going to go quite away, but if I make it here, it moves to the second thing. If I indent this, immediately the squiggle goes away. Okay, does that make sense to everybody? Right? More intuitive to some people than for others, but there it is. Also important, the capitalization needs to be exactly so. Okay, so both the name of the data type and those cases here that we're looking at, they all need to start with a capital letter. Yeah.
Why is the bar on line 21 allowed to be more left than the dog?
I'm sorry?
Why is the bar on line 21 is allowed to be more left than the
It only counts as it indented with respect to the first line. Okay? So not to the line before, but to the first line of the construct, right? And so that's how you can easily tell, is my construct over, is you just look for the first thing that starts in the same column or even further left.
So indentation is a binary state. It's either indented or not. There's no like levels of indentation.
No, there are levels of indentation, but we don't have nesting yet in this construct, right? So we'll get there eventually. But I mean, generally for obvious reasons, right? That's a good reason to keep nesting low, so that you don't get confused as to what belongs with what else. And sometimes people get confused about this. Okay, so far? So that's a very simple piece of data, is we can either have a dog or a cat or a snake. So this is a special case of a case analysis called an enumeration, right? And in a lot of languages, in a lot of other languages, in Java, in C definitely, right? Enums are a special construct. We will see that in Haskell is part of a more general construct, but we'll get to that, right? So now you could ask a question of a piece of data describing a pet. You could ask, is a pet cute, right? And I'm going to write down a little statement here for the thing that we're going to do. And for that purpose, we're going to write a function, right? And that function, I'm going to call it isCute, works like this. So I'm going to start by writing the type signature declaration here. Well, it's going to be a function. In goes a pet, and out comes a Boolean value, right? So true is going to mean, yeah, our pet is cute, and false is going to mean, no, it's not cute. Okay, so far? Question? Yeah? Okay. But you're okay?
Yeah.
Okay, good. So this here describes, so if you look at this, if you look at a type here that contains an arrow, right, that means that type describes a function. And on the left of the arrow is the stuff that goes in, on the right of the arrow is the stuff that comes out. So one way to do this is, well, the great thing about if you do your data analysis systematically, if you've written your data, if you've structured your data well, then the structure of your program follows the structure of your data. Okay, it's a very old idea in computer science, going back to Michael Jackson, actually. So, okay. I guess today's people, they don't go, Michael Jackson, who's this? So never heard of him. But there was a computer scientist called Michael Jackson anyway, so called Jackson Structured Programming. So the way that we're going to write it is, we're going to write it like this. So isCute, so we're going to call the argument here. Well, I'll get into details later in a moment. So the thing is, we know pet comes from this data type up there, right? You see this? And that data type says it's this or that or that or that. So we're coming from a case analysis, and if we want to do if we have a case analysis in the data, what we should probably do in the program is we should treat each case differently, right? That's why it's called a case analysis in the first place. Does that make sense? Okay? So we'll need a corresponding construct in our language to take apart the case, usually called a conditional or a branching construct or something like this, right? And in Haskell, that construct is called case. So what it says is, case pet, the way it starts is like this, case pet off. If you're coming from Java or from C or C++, it's a little bit like switch, okay? So, and the idea is very simple. You have different cases of pet, and you should list them all, and they should look like this. So I'm going to put it like this, and we'll get to the details again in a moment. So we've got we've got 3 cases up here, and therefore we should have 3 branches in the case here. Those things should all go together. Okay? So you might be noticing, right? I'm being very bureaucratic here. I sometimes call it the German bureaucrats' way of programming. Maybe I should call it the Swiss. Maybe the Swiss would do it differently, but probably about the same way. So the data definition has 3 cases, right? That you saw up here, 3. The code that goes with it has also 3 cases, and now the case statement that takes it apart also has all those 3 cases in it, right? Those things should always go together, especially if you're starting out. Sometimes people are going to get all smarty pants on this. No, I'm going to optimize. Don't do that yet, right? Just make things always align. Now you notice this is like a form, right? This is like a bureaucratic form here. So I can now fill in the correct values here where the 3 dots are. So for the purposes of this particular beginner's track, I'm just going to say dogs are always cute, cats are always cute, and snakes are not cute. Okay, so which is why if somebody had a snake here, I would have to choose it because they would very emphatically disagree. Okay, does that make sense so far? Okay. Question about this? Okay. I'm going to harp on this function a little bit longer. So first of all, we're going to try it out. And so one way to try it out is, again, to make one of those magic comments here. So minus, minus, and 3 greater than signs. I'm going to say is cute of dog, for example, right? And then I can push that button, and it will tell me, oh, yeah, dogs are indeed cute. I could also, add another one, is cute snake, maybe, to get a counterexample. And there, it tells me it's not cute. So that function kind of works. Okay, so far? Now, you notice, especially if you're coming from other languages, right? Haskell is a language by people who hate parentheses, right? And so if you're just starting out with Haskell, you can go around ZuriHac and you can say parentheses, good or no, and they will go, no, I absolutely hate parentheses. So that's sometimes good to know, to keep in mind when you're asking yourself, why is the notation the way it is? And in particular, you can call a function. You can see that I called that function without using the parentheses that are common in languages like Python or C++ or something like that. You just line things. You just make a little space, and you plug in the arguments there, and you can call a function. Okay so far? Any questions? So also, Haskell there's usually about 5 ways to write, different ways to write something, right? And so I'm sometimes going to tell you like how I like to write things, or sort of the primitive way of doing things. But I'm also going to tell you no Haskell programmer, no Haskellite is going to write this piece of code. Instead, they will write it slightly differently. So I'm going to comment out this piece of code like so. And you can see I can make a block comment by making a curly brace and a minus and a minus and a curly brace here. And I'm going to write that function again. And the way I'm going to write it is I'm going to make 3 equations. Question?
Before commenting it out, you might want to save the file.
Good point. Good point. Thank you. Yeah, always want to teach. Don't want to save the file. So hopefully you should see that show up now. Okay? So far, so good? So the Haskell people, they would write it like this. They would say, is cute dog. Well, first I'm going to write the whole thing, and then we'll see. They would just make 3 equations, right? And the Haskell compiler is just going to go and translate those 3 equations into that case state, that case form, that case expression that we see up here. That is the same. That is exactly the same thing as the thing up there, right? It's just the more. There's always a language is always the mechanics of the language plus the culture, right? And Haskell allows you to write it like this or like that, and the Haskell people, they will write it like this. So now we've got that very simple rule in that we should have, if your data type has 3 cases or 5 cases, you're just going to write 3 equations or 5 equations, 1 per case. If that makes any sense, right? So if this is generally the case in programming, but I'm just going to pretend that it's specific to what we're doing. Now let's backtrack a little bit to the moment in time when you weren't done with that function yet. So I kind of told you to do this, right? To put like 3 dots here. Now note, now I'm going to make it a little bit smaller just for a moment. I'll make it bigger in a moment again. If you look at this, right? If I'm, imagine for a moment that I'm not done with that function yet, right? So these equations, they come from the data type that we have up there. And this means that there might be an intermediate phase in the programming where I'm just writing this because it is something that I can derive from the type signature there, right? The type signature says an input to my function is a value of type pet. I can look up pet. Pet has 3 cases. Therefore, I need to write 3 equations like this. Does that make sense? Okay? And this is a very mechanical way to think about, or a very systematic way, or a very bureaucratic way to think about programming, is that I can derive parts of the program purely from the database, from the data types, when I'm not even thinking about the specific problem statement that I'm having. So I'm not thinking about cuteness yet. I'm just looking at the type signature up there, and I'm deriving pieces of the program, right? And functional programming in general really excels at letting you do this, right? As you structure your data, and from the structure of your data, you can derive your program. And if you do this long enough, you will only need to use a very small part of your brain to do this, which is important. Well, not important for you, but at my age, right? We're trying to preserve brain cells, and then I can do this. Okay, does that make sense? Right? And you'll get to my age eventually, and then you'll remember. Oh, Mike said, just do this automatically. So I can do this on autopilot. In Haskell, well, it'd be great if we could but you can see kind of that if I write the 3 dots here, right, I immediately get this stupid squiggle here, and then what happens is the IDE will stop helping me with my program. So if I've got something that I don't want to put in Haskell yet, I can put in the magic word undefined. And that's maybe the proper way to start this program. Okay? Yeah?
If you don't want to keep it undefined, I recommend to use the underscore. Warn you if you
see, people know stuff. Okay, but it also has a red squiggle. I think.
Yes, but it will not interrupt.
Okay. 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 I see. Okay. Well, good point. Let's try this. Let's run with this. So good. You already know there's people more knowledgeable about Haskell than I am in this room. Okay, so far. Yeah, but the point is our program is just not finished yet. We're going to put something in there, right? So what I would recommend is you first write those equations, right? And then during that time, you turn off, large parts of your brain and let them rest. Let those brain cells rest. Write down those equations. And now I can think about, well, a dog, is it cute, right? And then you go, so I'm going to call this the template. And I'll just leave that in there so that it's documented. And then I can kind of fill out, and a template is like a form, right? Like a bureaucratic form, and I can fill in the gaps now, and here's my finished program. Does that make sense to everybody? Okay, good. Now, let's move on to another classic example of functional programming. This is about, anybody who's seen a talk by me will probably have heard that. This is about animals on the Texas highway. Anybody from Texas here? So on the Texas highway, there are armadillos. And unfortunately, they're often on the highway because something happened to them. We'll find out. Okay? So what's relevant about an armadillo for our purposes is we're going to say, well, it is, it's dead or alive, and we have its weight. Okay? Now again, this is the beginnings of a data definition that we're looking at. But notice that it's different from the one before about the pets. Okay? Because, well, how is it different? Well, you notice that, with the pets, we had this word or written between those two things, right? Does that make sense here? Writing or? No. What word would make more sense? And would make, right? So an armadillo is not dead or alive, or it has a weight. No, it probably has both, right? So you might write the word and in between here, right? Or you could say, like, armadillo has the following attributes, or something like this. Okay, so far? So far, so good? Okay. Good. So this is not a case analysis that we're looking at. This is something else. This is called compound data. Or, yeah, we'll stick with that terminology for a moment. So this is called compound data. And again, whatever language you're programming in, you can ask yourself, how does compound data work in that language? And that's probably a good path to learning how that language works. So in Haskell, everything is sort of unified in that you also define compound data types using that data keyword. Okay? So I'm going to say, let's armadillo is kind of long. I'm just going to abbreviate that to dillo here. So we're going to make a dillo data type. And let me first type in the whole thing, and then we'll take it from there. And then I'll explain it, right? And so the way that we'll do it is we'll define what's called a record in Haskell. And what we want is well, let's do that for a moment. Let's suspend that for a moment. You will have noticed that there's an or hidden here, right? You see that, right? And you should all know how to translate that into Haskell by now, right? So this is no different from the pet, which could be a dog or a cat, right? So we could write, I mean, the only trouble is we kind of have to give it a name. So I'm going to call that liveness. And we're just going to say, well, the liveness is dead or alive. Okay. And then there's the problem of, well, what is weight? It's probably a number, right? Let's be really lazy about this, and I'm going to say this here, and this is a type alias. Okay. So the way to understand this is data makes a new data type, and type just gives a new name to an old data type. That's why there are different keywords. Some other functional languages are the same keyword, but here it is like this. Okay. Now with these two types, we can describe what is inside one of those Dillo values or objects, right? And so we can say, well, let me first type it out, and and then I can explain, and then save, and then I can explain it. I'm going to. Okay, so what does this mean? So I think we can all see that this, first of all, in structure corresponds to the thing up there, right? So let's talk about dead or alive. That's the liveness thing. And this is the weight thing. We see the appropriate types here. So what this just says is, well, Dillos are compound data, right? A Dillo object or a Dillo value is compound data, and it has two fields or two parts, and one of them contains the liveness and one of them contains the weight. So we can now construct values of that data type by just saying, something like Dillo1 equals, now this thing here, so mcdillo is what's called the constructor. And we'll sort of unify things in a moment. But so in the way we construct one of those records is we say mcdillo, we call the constructor, and then we say Dillo liveness equals, I don't know, alive, and Dillo weight, let's say 5, right? Something like this. Okay. And we can see that we've now created a value of type Dillo. Let me save that. Okay, so far so good? Yeah, question?
Is it necessary to have line 65?
Good point. So, question is, do you always need the type signature declaration there? And this goes for all the things that we had previously, right? And so you might have noticed, well, I wrote this before it was there, and the compiler suggested that I put it in. So I could also comment it out, and things there's no red squiggles. It works just fine. And I can do this also, for example, here, even here, right? This one I can leave out. Program still works. This is because Haskell has what's called type inference. So we'll figure out the types of values of variable bindings automatically. Okay? And when the first languages, became popular that had type inference this is an idea that goes back to the 70s, but they became popularized maybe starting in the mid-80s. People thought, that is so great, less typing, right? We can, we don't have to type those things. And you can look at papers from the 80s and 90s where people thought, this is so great, we can make short programs, we don't have to write the stupid type signatures because the program is correct without them. But this is good documentation is the point, right? So the structure of the data informs the structure of our types. And if we know the structure of our types, then we can figure out large parts of the program. This arguably you can kind of see it, but it's, as I said, at my age, I try to preserve. I want to preserve brain cells, right? And so rather than having to think, is it worth it here? Is it worth it there? I just put it in always, right? Easier for me. Your mileage might vary. But generally, I recommend when you're in doubt, put in the type signature. Even you will know it, but your coworkers, they might look at the program without the IDE. They might look at a printout if they're over 60, right? And they find it easier to figure out if there's a type declaration there. Okay. Okay, question there? Okay, no? Okay. Okay so far? All right. Yeah.
So the name of the type that we use in the typing is dillo. So
Yeah.
Mac dillo, what is?
So dillo is the type, right? And mcdillo is the name of the type of the constructor for that type, right? And if you're coming from a language like Java, then there's constructors, and the constructors there are usually called new and then the name of the class, right? And here you can choose the name of the constructor yourself. You can pick any name you like.
Could call it new dillo.
You could call it new dillo. Yeah, you could absolutely call it new dillo. You could call it make dillo. I can tell you that again, you could go ask Haskell programmers, do you like typing? And they go, no, we hate typing, right? And so the Haskell programmers always like to type less. Sometimes to the detriment of the understandability of the code, but here, I've never seen Haskell programmers actually spell out make here, even though arguably maybe they should, right? If that makes any sense. What Haskell programmers will more commonly do is they will, in this case, where they will just call the constructor the same as the type. And I find that slightly confusing at the beginning, but maybe if you're thinking about this, right? And so Haskell has this two-class society, in that there's the values have names and the types have names, and those two namespaces are separate, right? And if you go, well, you're not in the dependent, by definition, you're not in the dependent typing class where those worlds merge. So we'll keep them nicely separate here, okay? So dillo is the type and mcdillo is the constructor, and that distinction will become important later. Now, you can imagine, so this tells us how to make a value of type dillo, right? It does not tell us how to get things out of, if you imagine sort of the dillo object as a box where you put things in, it doesn't tell you how to get things out, right? And the way that works is in sort of a lot of sort of OO languages or in C or something, you would put a dot there. And here it is slightly different in that dillo liveness is what's called, let me first write that down, dillo liveness is what's called a selector, and a selector is a function. So if I say dillo liveness of dillo 1, so it's, then a problem occurs. So we'll get to that. We'll get with that problem just a moment. But first of all, yeah, let's solve that problem. When you see this error message, it says it's very mysterious. No instance for show liveness arising something, right? But if you see this no instance for show liveness, it means you need to add a magic line to your data type definition. If we're lucky, I can explain to you what that line means. And that line looks as follows. It's always the same line. It says deriving show. Okay? Now, I did that deriving show. You can see a red squiggle. Yeah?
You want to add it to the liveness.
Yeah. I'm just telling you how to get there, right? How do you know that you need to add it somewhere else? It says no instance for show liveness. So it complains sort of in the same way about another type, about show liveness, which we're using here. So I'm going...
Actually the same type.
Huh?
It complained before about that very type.
Okay. So anyway, so it told me that I still need this, right? So when it says no instance or show something, it means we add that line deriving show, okay? And that will... the main thing that it will do is it will make the error message go away. So if I push the refresh button here, it will tell me, okay, alive, and it... if I go dillo weight of dillo 1, then it will tell me this. Maybe we should make a second. We'll make a second one in a moment. So this means so you can also ask here, what is the type of something, right? And so if we ask, for example, what is the type of dillo liveness, and do this in a magic comment, it tells us that dillo liveness is a function. In goes a dillo, one of those boxes, and it gets us out the liveness field, if you will. Okay, does that make sense? Yeah. This is something built into the Haskell language. And unfortunately, so one of the problems with learning Haskell is that advanced concepts, and this is unfortunately an advanced concept, creep in early, and this just happened. So hopefully we'll get to the point where I can explain it, but I'll need more time. So for now, we're just going to treat it as a magic thing that makes the error message go away, right? Okay, so far? So far, yeah. Let's add. Now, imagine it's kind of, you can imagine you want to make more, more armadillos. It gets to be a lot of typing, especially if you're like on a German keyboard that doesn't even have German Mac keyboard. Anybody, right? That doesn't even have like curly braces printed on keys, right? So the Haskell programmers will want to abbreviate this, and they could do it like this. So they could go dillo2, and we could make maybe a dead armadillo, and make it 8 kilo, like this, okay? So you can just list the attributes in the order that they appear in the record definition and leave out all that funkiness with the curly braces and the selector equals to something like this. This means exactly the same thing, right? If I then ask, dillo2, what are you? Then, oops, sorry. You'll leave a line here, leave a blank line, right? Then it will give me the full thing here that I see this. You also see that the thing that it prints out could also be something that I plug back into my program, right? It uses the same, printing it out uses the same notation as constructing it as part of my code.
Is it possible to have multiple constructors for a given type? Maybe with different arguments or even like completely different structure? I don't know if it makes sense, but...
Short. I think that short answer right now is no. Okay. Yeah. But keep it in mind maybe, and ask me again a little later when you feel, okay, there's something there, right? Yeah. So in Java you could have multiple constructors or something like that, but in Haskell you only get that one, right? And I should note that, if you're programming in Java, right, they just added something called records. This is exactly this, right? So they added the same thing here, and there also you only get one constructor, right? Yeah.
Can you scroll upwards for
Yeah.
deriving?
Yeah, here. So this is that line here, and that line, line 57, and line 63. You're kind of going like this? Do you have a question? No? Okay. You just don't like what you're seeing. No, it's okay. It's okay. Do you have a question?
Question on line 59, if it's not too much for a little.
Yeah.
Does Haskell have something like new types in the sense of I want my way to be an integer, but I don't want it to mix with other numbers?
Yes, it does. It's actually called new type. But again, we don't have enough quite yet to explain it. But if you ask me about it later. But it kind of goes trivially out of the other stuff that we're doing. Yeah?
I missed the part about deriving show and why we did that because of the
I can't. So this just made error messages go away, right? So actually, if I deleted, let me delete it. Let me get rid of this one, right? And now if I go and push this button here.
That's the liveness.
That's the liveness. I'm sorry. I need to comment on both. Yeah. Okay. Good point. So let me do that, and I push this button. Then an error message occurs that says, no, it mentions show. That's the important part, right? If you see that it mentions show, that means, I forgot a deriving somewhere, namely deriving on the data type liveness. That's what you meant. Okay. Yeah. Because it mentioned that type. Yeah. So if I then put these two things back in again, and I do this again, then it works, right? And yeah, I see you have questions about this. So what it means is the following: show just means enables the IDE to print values of that type, right? And so if you don't have it, so essentially it complained, well, yeah, what you did was all right. Something came up, but I can't print it, right? Or I can't show it, right? That's why it's called show. Yeah, question?
Below liveness and below it act as functions, and we call them, we just get what.
Yeah. 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 Question?
I guess, how does this go with generics? Like, can we
can we just have, I don't know, some general type def thing, and then we just specialize it for our type or something?
Yeah, absolutely. You can do that. We'll get to that, right? Okay, but so far so good. So what we have here? Okay, yeah.
I noticed when you have your primitive type,
Yeah.
you put like derive show primitive.
Because somebody put it there. So somebody, I mean, the integer type is defined in the standard library, and somebody already put the equivalent of deriving show there, right?
When we put it in a deal,
Yeah,
it doesn't compile
yeah,
properly.
yeah,
You still need to go all
yeah,
the way.
yeah. So we'll find out that a lot of goodies sort of are already implemented for the built-in types. That's one of them, right? So the built-in types already know how to print integers. It'd be really annoying if we had to implement that. Right. Okay, so far? Okay. Now, moving very, 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 very fast. Maybe you suspected here there's something missing up here, right? I said animals on the Texas highway. Okay, there's let's program first. Well, I'm sorry, let's program something here first. Because what happens to the armadillos on the Texas highway is trucks run over them, right? And then they're dead. Okay. So now this tells you, somebody mentioned immutability in the beginning. So we want to do like a function, let's call it run over a dillo. So it runs over a dillo, right? And if you are programming a language like, I don't know, C or Java or something like that, you would just go and set the liveness field to dead, right? That's what you would do, right? So, and the return function, the return value would be like void, right? And you already know, now the thing is with void, right? If you see like void as a return type and a type signature in C or Java, if you're coming from those languages, you know that those functions are doing something that the type signature doesn't tell you about, right? So if your function changes some data, right, the type signature doesn't tell you what data it changes, right? And if there's a void there, it says, well, if it doesn't change anything, why call it in the first place? So, of course, any function can do that. Now, here it is different in that, well, we can't, as you noticed, right, we've got the selector. The selector is like a getter function, I guess you would call it in Java. There's no setter function. There isn't one, right? And, you can go to the Haskell committee and say, put in setter functions, and they'll turn you down. Say, no, we are a purely functional language in the sense is that we won't allow you to change data after you've created it. So what you're going to have to do is, the way that I think about it is this, right? Imagine you are sitting in that truck, okay? So you see the armadillo in the distance. It's just starting to cross the highway. It's really, look at pictures. They're really cute. They're really nice, right? And you kind of go, oh, right? Your phone rings, right? Of course you go. You're slightly distracted for a moment. Your truck goes like this, right? You look out the back window. The armadillo is now dead, okay? So, okay? But you remember the live armadillo from a moment ago, right? You remember that, right? Do you understand that your object-oriented void returning, object-oriented program does not remember the live dillo, right? So it's heartless, essentially, right? So what we're going to have to do, so the way that we need you to think about this in terms of the way to conceptualize what we're dealing with, the data, is not, the dillo values do not represent the armadillo. They represent the state of the armadillo at a certain time. So if at a later time there's a new state for the armadillo, you need a new representation of that state, if that makes any sense. It's a little convoluted, but it is closer to the way the brain works, right? Our brain, we don't perceive the armadillo, right? There's some visual, there's the memory of what we saw. And that is more like the way your functional program works, right? So we're going to need to return a new dillo value. And the way we can do this is we can do it like this. We can say, well, so what happens here is well, we need to, so out comes a new dillo value. We know there's only one constructor for the dillo, so we need to call it. Does that make sense? Right? If a dillo value comes out, there's only one way to make dillo values. That's to call that one constructor. that exists, right? So I'm going to call that one constructor, right? And I'm going to, well, now it's like a form, right? The form is like Dillo liveness. I'm going to put an underscore here now. And Dillo weight equals under. So that would be, you know, the government-approved form for creating armadillo values. Does that make sense? Right? And now we can ask ourselves, well, what is, you know, how alive is our armadillo after we've run it over with a truck and we go, oh no, it is dead, right? And then we go, well, how much does it weigh? And then we would, well, this is kind of a definitional question, depending on what your truck, how heavy the truck is. But we're going to pretend that it's just the same as before. So I'm going to call the selector and do this. Okay, so that would be a way to do it. And again, we can try out our function, run over Dillo of Dillo1, for example, right? We see that outcomes, I'm going to spell it right, like this, right? It weighs the same as before, but it is now dead. Okay. Any questions so far? Okay, so.
But we can't leave it out.
Huh?
We also need to reference the constructor, the selector. We can't leave it out the weight.
Let's try it out. See what happens. You mean like this, right? So, well, you can see there's a squiggle, but it's yellow, right? And what does the squiggle tell you? It says, you forgot a field, right? But it's only a warning, right? This goes, don't do this, right? Specify everything. Now, you might ask, well, you might say, well, but Mike told me the Haskell programmers hate to type stuff, right? And this is a lot of typing for that simple sentence, the armadillo is now dead, right? And so, of course, and I also told you there's 5 different ways of writing everything in Haskell, right? So let's get into those 5 different ways. So one way to do it is we can use the same abbreviation idiom that you saw above, right? And so maybe we could go like this. We could go mcdillo, dead, and then we write Dillo weight of Dillo, like this, right? So see that is the same idiom as above, where I just wrote make mcdillo dead of 8, I think, right, for Dillo 2. Okay? Note that I have to put, I told you the Haskell people hate parentheses, but here you have to put parentheses, right? Let's do away with the parentheses like this, right? And so this is a common mistake that beginners in Haskell make, is because the language hates parentheses, they think that they never have to put in parentheses, right? But if you look at this, you just see, 1, 2, 3, 4 words in a row. There's no further syntactic structure, if that makes any sense, right? It's just 4 words in a row. There's nothing to indicate that those two things belong together. Does that make sense? Therefore, you need to put parentheses. Okay? The Haskell people, maybe the real Haskell people, no, not me, right, that are at this conference will tell you, no, Mike, bullshit, you can put a $sign here. Yeah, well, if you want, but I understand parentheses. So I think we all understand parentheses, right? Okay, so far? So I hate even these parentheses, but I don't. So there we go. So that's a way to write it shorter, right? So there's another way to write it shorter, which is to say, well, what you often have, I mean, you can imagine if we deal with state like this, in that we have the armadillo, the state of the armadillo before and the state of the armadillo after, and something happens in between. In practice, sometimes you'll have a record that has like 7 fields or 9, well, hopefully not 9, but maybe 7, right? And only one of the fields changes. Right? And now I just told you, well, you have to provide values for all of the fields. Right? That's a lot of typing, but you can avoid that typing with something called a functional update. And the way that looks is like this. You write Dillo. So this is the thing from the left-hand side. So, right? So, and then you can say, well, I want a copy of this record except for the stuff in the curly braces, where I go Dillo liveness equals dead, right? Does that make sense? So that will also, so those definitions that I'm writing, they're all the same. Okay, so this will just copy all the fields over except for the liveness field. And that will be dead, but the weight will be the same as before. Okay, so far, so good? Question?
Where's the weight defined?
You mean for the output of this function? It comes from this, right? Notice that this is, maybe the way to write this clearer is to just name it D, and it has to be the same here. So what this says, so D followed by these curly braces means make a copy of D, including the weight field, except for this thing here. No?
I don't see where's the weight.
So this construct here, D followed by the curly braces, says make a copy of D. So maybe let me put it like this. So if I did away with this, do you see here where the weight field comes from? Comes from the input. Yeah? Okay. This is the same thing, only it tells you, this is the same thing. Make a copy of D except for the liveness field, and that you set to dead. Okay? So I really like that you keep asking, okay? Everybody else, do it like him, okay? Poke me until it's clear. Hopefully it is clear now, yeah? Okay.
Is this in a way just saying return D, but now it's not like you're overwriting the low liveness to return dead?
No, the D, this makes a copy is the important thing, right? Is so, because you can't change values, you can only make copies of values.
Braces here are something just has a special meaning in this case.
Special piece of syntax, yeah. Right.
Is it a deep copy? Does it move, or it involves?
What is a deep copy? What is that? What is a deep copy?
Pointer stuff.
Is it like copying the bytes, or it's constructing the objects again?
How would you know the difference?
For performance.
Then no, it does not do a deep copy. But operationally, in the sense of would your program produce different results, in Haskell there's no way to tell the difference. And that is good, right? So that, it sounds like a simple question, right? But this thing is really deep in the sense that if we can't ever mutate, change data structures after the fact, right? Then it makes no difference whether we're holding the thing or its copy. And this also is the secret. I'm probably not going to explain this later. I'm probably going to, this will probably not come up later if nobody asks about it. That's why I'm telling you about this now. This means that the secret to data structures, right? So obviously if we have data structures like a collection, like a list or a map or something else, right? The way that we manipulate it is if we want to add an element to a list or something like that. You can't do that. You can create a new list. Right? But because you can never tell the difference between a thing and its copy, you can reuse the original list and the new list, thereby sharing most of the memory that they use. Right? And that's the secret sort of behind high-performance functional data structures, so-called functional data structures. Right? Okay, so far? Okay, question?
One comment, one question, the language construct.
Yeah.
As for the comment, there's a nice quote from the guy who did
Yeah.
which prefers immutability.
Yeah.
He basically says, well, if you're writing in Java, say you're watching a baseball game, imagine it would be programmed in Java. If you wanted to take a picture, you had to freeze the whole stadium. Like everyone has to freeze, and you can make your picture of the state the game at this position. Whereas if you work like this, you basically go, Chuck, I've got my photograph, that's it. The thing happens in the background.
Yeah. Yeah, I also like that analogy, right? In the sense that when we perceive things as humans, right, we don't perceive the thing, right? Our brain takes a snapshot picture that we can sort of examine for a few milliseconds, and therefore we don't notice that things really in the real world are always moving. Right?
As for the language, is this a language construct?
Yeah.
Or is this more of every instance of a DLO is secretly also a constructor for Dillo? Because it looks like
No. Yeah. It looks like no. This functional update is a separate construct in the language. Yeah. Okay. Now the tricky bits. So still, probably the Haskell people would not write it like this. There's another way of doing it with something called pattern matching, which we've seen, but maybe not seen, and it looks like this. We write as if we were constructing the object on the left-hand side. Like this. So that maybe gives us a hint. Dillo weight equals, I'm sorry, not Dillo liveness equals dead, like equals L and W, like this. So what this means is, well, this is what's called a pattern, right? And if you kind of, well, should have brought up the overhead projector, then we could have kind of made a slide with this. Yeah, but it's got to continuous. I need 2 slides. I'm okay. But you see this notation here, right? And you can kind of superimpose it here. And what this means is, well, the input has to be a Dillo, has to be a McDillo, an object created by McDillo. And here you can see I put those names here, L and W, and those get bound to the corresponding parts of our Dillo objects, right? I always feel like I'm a little hand-waving with this explanation, right? So this means, this is the same notation that I would use when I'm constructing the object, but I only put a few placeholders in there, and they will get bound to the corresponding parts of my data. So and then I can write McDillo, McDillo dead and W. The underscore is still there. It's just not visible, like this, right? So I don't have to type out the call to the selector. I can just use pattern matching to do this. Okay, this is a little bit more idiomatic. Does that make sense to people? Okay, so that's really an idea that really originated with functional programming, and that has only recently been introduced in other languages such as Java. Does that make sense? Okay, so yeah, question?
Can you do the pattern matching positionally, just like you did?
Yes, yeah. So the thing is, right, I told you we use the same notation here as when constructing things, and I told you this abbreviated notation for constructing things, and we can also use that for pattern matching, and that would probably be the sort of idiomatic form. So that's what it will look like. So we could also go run over Dillo, but then important, so maybe before I go here, everybody can realize that, let me copy this. So we see the differences, okay? So we can see here that we never use this thing here, right? We could also leave it out. Does that make sense? Right? Huh? I'm sorry, it's the armadillo, it's going to be dead afterwards. It doesn't depend on the fact whether it was alive before. So if you go with your truck, you've just gone over the armadillo, and you're going backwards, just for fun, right? It has no effect, right? The armadillo is just as dead as before.
That makes sense. It's just now it kind of looks like you're calling the constructor with only one input.
Yeah, it does, doesn't it? But you saw before that I could do this. I would only get yellow squiggles, right?
Yeah.
So the point is, but mechanically, okay, but but this only works because these things have names. That's the point. Okay, so I can use an abbreviated notation that looks like this. So if I do it like, by the way, I'll get to that. So we've got the liveness and the weight, right? And now I can go McDillo dead weight, and this would probably be the idiomatic form that we would see in Haskell. Now note that here everything is positional, so I have to list all of the attributes, even though I'm not interested in the liveness. Does that make sense? Yeah? So what the Haskell people would do is they would say, well, let's be explicit about the fact that we don't care about what it is here. Then we can put an underscore there, which just says, I don't care about the value that sits there. And the Haskell people love to use single letter identifiers because they hate typing. Ask them, right? I recommend that you spell this out. Okay. And you'll see, if you don't believe me now, look at a bunch of Haskell code that the people out there are writing, and then tell me again. Okay? Okay, so far? Good. Any questions so far? All right. Let's do one more thing so we can cover the core, and then we'll maybe do a 5-minute break. Here is the thing. I told you up there, I told you there's animals, and then I just told you about armadillos. Maybe there's other kinds of animals on the Texas highway, right? Now, so maybe there's like an armadillo. There's armadillos. An animal on the Texas highway is either an armadillo or, let's say, there's a snake, right? What's the correct word to put in between those two things? Or. Okay, so this is a case analysis that's going on here, right? Now, the point is, case analysis in Haskell, so ideally, I think sort of mentally, what I'd like to do is I'd like to talk about snakes and then come back and say, well, I've talked about armadillos here. I'm going to talk about snakes somewhere else, and then I'm just going to make another data type that says it's an armadillo or a snake. That does not work in Haskell. In Haskell, all the alternatives in a case analysis have to be part of a single data type. Okay? What does that mean? So let's see. So we have to effectively, when we do this, when we add, so what we're going to do is, well, maybe let's leave this here for documentation. And so what we really need is we need a data type. I'm going to call it animal, okay? Because we have more cases, right? I don't know, it reformatted things in a terrible fashion. Let's do it like this. And then we can say snake, right? And
You already have pet snakes.
I already have pet snakes, yeah. Let's call it mix snake, right? Let's do parrots, after all. I usually do parrots. Let's not get too confused. So it's a mick parrot. And these are all, and these are all speaking parrots, right? So they'll all have a sentence to say, and they'll also have a weight. And you can see here that I can further abbreviate things by not declaring an explicit record with curly braces, but just mentioning the types here. And this means that only the abbreviated notation is going to be possible from here on for this particular case. Does that make sense? Okay. So note, this is the type, right? The type is now called animal. I renamed it. And the type now has two cases or two constructors called mcdillo and mcparrot. And if you look back on our very first data type with the pet, right, you can see this is all part of like one unified construct. So because you can see here both of those cases have attributes, but if you imagine removing the weight and here the string, then, well, it'd just be a case without attributes. So the dog and the cat and the snake at the beginning are just cases without attributes. So enumerations are just a special case of this thing, which is called an algebraic data type. Okay. So now note that we have to fix things up a little bit. So there's a couple of red squiggles. Because Dillo1 is now no longer of type Dillo. I just deleted the Dillo data type, right? It's now of data type animal, and it's of data type animal here. And then, of course, this one goes from animal to animal. Okay. But now,
Only run over.
huh? Yeah. So. Okay, so far? Okay, do you understand it so far to this point? Now we see, well, there's yellow squiggles here if we look closely, right? And our run over Dillo function has changed types. The type no longer mentions Dillo, right? Instead, it's supposed to, the only way we can do this is we can only make it work on animal. And there's two cases of animals now, right? There's parrots and there's armadillos. right? And here it complains, well, you forgot one case, right? Remember what I told you? Each case, 3 cases, 3 equations, 2 cases, 2 equations, 5 cases, 5 equations. So in this case, there's 2 cases, and the other case is the parrot, right? Run armadillo, parrot. And what is it? It had a sentence and it had a weight, and we're just going to go make parrot. And well, what happens to a parrot when you run over it? It shuts up. And do it like this. Okay. So far, so good. Okay. Yeah, absolutely. Sorry. Yeah, now it's saved.
Now that you have created this animal type, is it possible to write a function that works only with the dillo? I guess not, right? Because there is
no, you cannot do this anymore, right? So this is a way of doing things that has trade-offs, right? It's not obviously always good or bad, right? So there's a lot of you often have you sometimes have situations where you would just like to write things separately, define things separately, but what is important is really every case needs a constructor, right, that you need to name, right? You can't do without that. And each equation here needs to mention that thing, right? And all the constructors, all the cases need to be in one place in Haskell. And that gives you a great deal of programmer convenience. It sometimes is to the detriment of modularity. And then you've got to use fancier constructs. But it's got this is a very sweet spot sort of in the ergonomics of software, of programming language design. Because if we talk more, if we had like a couple days to, to look at all kinds of real-world scenarios about data modeling, this gives us a special template for data modeling, right? It says, well, when you're looking at a thing in your domain, you think, first of all, you think about the different forms that it might have. Is it this, or this, or this, or this, or that? And then each individual case could have attributes, right? So it's or this, and this thing has that attribute, and that attribute, and that attribute, and that attribute. Now, I'd like to tell you that this was because, they did this because it is a common pattern in many domains. Because, no, it was designed for sort of mathematical elegance in that way. But, so I'm probably not going to get to theorem proving, but the relationship, implicit in that is the relationship between functional programming and mathematics, right, that we have. And maybe some of you are going, oh, mathematics always hated that. It's why, I got into computer science, so I would not have to do mathematics. I have bad news for you. I think the thing that we should be aware of is that, humankind did domain modeling especially for communicating among people. The thing that we did for domain modeling before computers existed was mathematics, literally, right? This is why, in a lot of ways, why people were doing mathematics. And so mathematics over time has developed sort of, I'd like to call it patterns. Those are patterns that the human brain is amenable to, right? They don't exist outside of the human brain, right? And this is why, and when we're doing domain modeling, we're not really modeling the domain, we're modeling the way, I'm going to stop with the esoterics in 2 minutes, but, right? We're not modeling the domain, we're modeling the way that we think about the domain, right? And so mathematics gives us great mental tools to organize our thoughts, hence to organize our thinking about the domain. And this is why, things that have mathematical elegance often coincide with being of great use when we're doing things like domain modeling and programming, right? Not because this is some, there's some structure to the universe. No, it's the structure of our thinking that's important here. Okay. So, so this is now the basics. Yeah, sorry, question. Yeah.
Before you define the pet as cat or dog,
Yeah.
couldn't you have defined animal in terms of dildo or parrot, and so still having a dildo?
Yes, but each time, yes, you can do that. But the point is that here, each case needs to have a new constructor, right? So you can do that, but it means you add a level of you have to add a level of constructor. So, for example, if you did this, imagine for a moment that you wouldn't So that you've done this, right?
Still create the new constructor, no? We just
Yeah.
put them in the animal in all. But we still have two constructors.
Yeah, but you can't sort of reuse the old constructors. That's the point, right? So if I go animal here, so I have to, I can't write Dillo parrot. That doesn't work. Even though it seems it should, right? It does. That does not work. So what you have to do is you have to think of a new constructor. You've got to say, a animal Dillo and animal parrot or something. So you have to make up. So every case needs to mention a new constructor, or every case needs to mention a constructor. Period. Right? Huh? We always did it. We always, even here. I mean, I think you mentioned this, right? This is also, each case has these things. The Haskell people would call these people, these things would call also these things constructors, right? It's just that they're nullary constructors, right? So effectively, they're constants, okay? Right? And so, I mean, some languages are what's called union types. There you could do something like this, but Haskell is not among them. And that's, I think, for the better, and this is a very focused sort of, so this concept of algebraic data types, also very old, dates back to 1980, pretty much. But it's just this very sweet spot of ergonomics, and it fits a lot of situations because of its elegance. And sometimes when you go beyond it, then you've got to use funkier constructs. But this, the first year that you use Haskell, run with this, right? And then you can go from there. Okay, yeah.
So to have something like a subtype, for example, having the pet also be an animal, you'd have to either make a constructor for the generic pet or for each of the pets.
Yeah. It gets you into all sorts of trouble in programming language design, right? So you get into something called subtyping, and let me tell you, this is pure hell. You don't want to be there, right? Yeah.
So I guess in short, we can say that types can't overlap. There can't be values that are in two types.
There can be values that are in two data types that you've defined yourselves, right? Somebody mentioned there's generics, and you can have generics and function types, and so you can have two types that are instance of each other that overlap, right? But yeah, that's the short version. So what we've seen, no, but in general, yes. Okay, so this is, I think, the essence. Let's take, so it's 15:08 now. Do you think we could manage to reconvene at 15, well, if everybody takes a little break and chat, 15:20, okay? Because, okay, 15:20, we will all be, I will start talking at 15:20 sharp. So do whatever you want until then.
Do you want to take a break as well, or can I ask you a question?
No, you can ask questions.
About the idiomatic way of creating a new object, right? You said that the positional one is the most idiomatic one.
The one? I'm sorry?
The positional pattern matching is the
Yeah,
most idiomatic way of
yeah.
But it looks to me that if somebody goes to the step definition and swaps to
Yeah.
then you're in trouble, right?
Then they are in trouble, yeah. And
Why is not more idiomatic to just specify what is the thing that you want to change, and then you're safe against it.
So there's a couple of things here, right? And so you can easily imagine ways of screwing that up, right? And so the first line of defense against that is to use rich types, in the sense that you have types that distinguish between different things. So if you find yourself having a constructor that has arguments int, right? Then your type system won't help you, telling you the wrong order from the right order, right?
This is a bad problem. But then you still have, even if you switch types, then you still have to fix your code, because the compiler is not going to compile, right?
Yeah. So
if you specify the thing that you want to change, that function is going to compile.
The functional update. Yeah. Yes, that's true. Yeah. So and why is the
positional approach preferred over this?
Because the Haskell people generally consider the records not so good design, which is why they tend to avoid using them, right? Now, of course, which is why, especially, I mean, you can imagine, if you've got two fields that really have different types that really identify what you're doing, then there's no strong reason to make a record, give names to those things. Yeah, right? If you've got 7, then you should do a record, right? If you've got 4, you should probably start doing a record, right? And so then that goes to a larger question as to, that is going to predispose the way that you do data modeling towards things that have fewer attributes rather than more, right? And that's sort of the larger space of sort of functional design, right? Yeah.
I have a question about teaching those big sum types.
Yeah.
Because you use those record accessor functions in like big sum types.
Yeah.
And the problem is that those are like non-total. If you call the function, then you get a record access exception or something like that. So I think if naively, if I had taught it, I would have done the thing where you have to have the annoying second constructor that you have to somehow name. Like your armadillo or whatever you just wrote. What would you say is the trade-off there? Would you?
Well, I mean, you can avoid all of that if you never call the selectors explicitly, and if you just use pattern matching, right?
Okay, but then, so that would just be an argument against this record syntax. Because, like, if you do the position,
maybe,
yeah,
but the problem,
then it's okay again.
as in teaching, there's also trade-offs. At this point, right, I wanted to first explain records independently of the rest, right? Okay. And that was the main point there. And there, really, if you're doing that, if you just have that situation, then first of all, you really should think in terms of, what are those fields? What are good names for them? Because a lot of the time in Haskell, that just doesn't happen, right? People don't think of good names because they think, the position is the position identifies which one it is, right?
I'm always a little bit conflicted.
Right.
Sometimes I think the Haskell programmers always hate on type synonyms. I think sometimes they might actually be better. Yeah, and so that's also sometimes something I've learned sort of from the larger software architecture and domain-driven design community is that it really is. Yeah, the shorter names are shorter, right? But you tend, my pet example is we often look at a case study, look at something called Xmonad, which is a window manager written for X windows written in Haskell, which is really beautiful in many ways, right? But the if you look at the no. But people were fiddling with that as though it needs to be on for this to work or for the recording to work. Okay, no.
For recording,
all right.
I guess these computers do recording.
You see, if you have the
let's just leave it.
Yeah, let's leave it. Let's not fiddle with it. So if you want to see something here, here's a central type in Xmonad, right? See what I'm getting at? So which one? It's a window manager, right? Which one is for Windows? Well, it's A, but right?
What is the I for?
I don't know. I forget. I think you're going to have to look somewhere down. I forget what it is. But you see the problem, especially because, as I said, it's a beautiful code base, except for that one bit. Especially because you think, surely there's a comment that explains what those type variables are, and there isn't.
Yeah, I think
right?
that is just
right?
But
right.
At the same time, I think this is nothing for
I can understand it in functions like flip. Are very abstract in a way.
No, of course, for abstract values, right? For abstract things, it makes very good sense to not. This has a flip side, right? If you have things like type variables, especially things that are typed, and you don't know what the type is, right? There's nothing to say about them, so you should not say anything about them, right? And you should make it very clear in the name that no, I'm not, right? I'm not saying anything about that, right? But if you have something to say about something, like, for example, this is the window type parameter, then just call it window, please, right? So yeah, but the Haskell people often feel differently.
I think that is sort of I just think this is not good code, and I think you can write that code even in Haskell.
Yeah, but I'm saying I'm just telling you the Haskell culture, right, is to write these one letter identifiers,
but
right?
I think you can also like go too far in the other direction. Where sometimes like a higher kind of data pattern can be good. It can be terrible for compile time. It has like tons of trade-offs in directions that are like not obvious if you're a beginner. I think. But there, a type parameter can give you a bunch of.
No, absolutely. Type parameters are great, right? But if they have a certain role, you can give them a name. Give them a name.
Yeah, absolutely.
Yeah. I'm sorry.
I have a bit different direction of question. So when you said something about the generics and subtyping and that it's hell, I agree with that subtyping is hell.
Yeah.
I have more like philosophical question, like okay, so sometimes we would like to group things together, right? Like we would like to say that this type follows this generic pattern, so it like must implement like these things. But we wouldn't like explicit subtyping because explicit subtyping would like import the definitions from.
Would you like something like an interface?
Yes.
So, that exists in Haskell. It's called a type class.
Okay.
Kind of.
No, there's an interface.
I guess
a better answer to that question is a record type. But we'll maybe get to that.
Like from language design perspective, what are the options to like get around this problem? That sometimes we would like to specify that yes, this must be present here, or like we would like to group this because, for example, we can have error type, right?
Yeah.
I guess that's commonly used, right? And we would like to say, okay, this is the message of an error, and every error type must implement this.
Yeah.
Like that. Right.
Yeah, make a record type.
Okay.
Yeah, but just make a record type.
We have record.
Yeah. Don't make a type class.
Maybe I misunderstood what you meant by must be there.
Yeah.
I thought you mean that the type like must follow certain rules, and there's several types that must follow the same rules. Then a type class makes sense. But if you have just like one type that says, well, here I need a bool and here I need a string, that's a record.
I meant it like, for example, with the error type, right? Like, let's say we have algebraic data type errors, right? So on some left, we always want to put some sort of error, and on some right, we have success of our computation, right? And so when we, for example, end up the whole computation stack, we end up with either some left or some right, and on some left, we want to like print the thing, right? So it must be showable, for example, deriving show or deriving message or something like that.
Yeah. Make a record type.
Okay.
And you can give types constraints, or you can give individual constructors constraints. Forget there's some language extension that will let you do it, but and that will package the functionality in those that you mentioned with it. Yeah. Sorry, I'm looking at you funny because I'm trying to think about how I'm going to fit all that stuff in the remaining time.
No, I'm good.
So, all right, folks. You want to hear what I have to say? Go sit down.
With extension codes if you need one. I'll get one later.
So, I'm going to, so hopefully somebody asked about purely functional, and I feel we've covered that at least to some sort of superficial degree with those running over functions, right? So in the sense that you can't change your data type. This extends to the fact that everything else where you do the same thing and you would get a different value out is usually not allowed in Haskell. So the idea is in Haskell, when you write an expression, it will always return this, or if you call a function, it will always return the same output given the same inputs, right? And in order to, this implies, of course, that in order to have programs that do stuff is something different, right? And needs to, doesn't really fit into this paradigm. So I'm just gonna, so yeah, we have limited amount of time left. I will try to, I'm sorry, do we need power?
Yes, but I cannot plug it in because the whole is
This one, that one is also broken?
I'll bring some extension codes.
Okay, or, okay.
There's one here.
There's one here. Let's,
Extension code.
okay, does that, okay, more is coming, okay. All right, so you might have noticed our run over Dillo function just has one input, right? And you can also have functions that have multiple inputs. Let's write one like this. This is very, okay, here's something else sneaks in. Now this function here, I mean, I think if we just look at this equation here, we can kind of see what it's trying to do, right? It adds two numbers. That makes sense, right? So we can call it. Let's call it. Right. So this would yield 7. Okay, that's pretty trivial. But maybe you're looking at the type signature here and you're thinking that looks a little bit funky, right? Does it look funky? To whom does it look, or does everybody say, okay, no, that's totally clear to me? Funky? Funky? Arms up? Funky? Couple of arms? Okay, totally clear? Okay, that's not the exact compliment, but I'll leave it at that. So the way to understand this, so first of all, the thing that you have to understand is that Haskell only ever has unary functions. So every single function in Haskell is such that one thing goes in, one thing goes out. It's symmetric, right? And now this sort of goes contrary to what this suggests, is that you can have functions that have multiple inputs. But the way to understand it is by understanding that this arrow up here associates from the right. So the correct way to parenthesize it, again, the Haskell people hate this, but I'm going to do it anyway, right, is this. So what does this mean? It means that f is a function. So now this, hopefully, maybe we can read this, right? It says f is a function that accepts an integer that returns another function that accepts another integer, and that returns an integer. So the way that functions that have multiple inputs work in Haskell is they work in what's I would call maybe a staged manner, right? So you've got 5 arguments, 5 inputs. The way it works, it takes the first input, returns a function that takes the second input, that returns a function that takes a third input, and so forth. Okay? So that after a while, after you've seen this a couple times, right, you just kind of gloss over this when reading it, and you think of, when you see these multiple arrows, you just think about it as those things are all inputs except for the last one, that's the output. I could go into more depth here, but that will keep us from covering some of that other material, so I'll gloss over that. These functions are called curried functions, named after a mathematician called Haskell Curry, right? So, and we could spend an hour going over this. There's really neat stuff, but we're not going to do that right now. Okay? So that we get to at least some of that other stuff here. Okay? Now, Haskell, all function languages have a data structure built, a collection data structure that comes with them that's called a list. Okay? And it's always, it doesn't matter if you're looking at OCaml, F#, Erlang, Scala, Haskell, whatever, when they say list, they always mean a specific data structure. So it's different from Java, for example, where list is an interface and there's multiple implementations, right? In Haskell, or in functional languages, it's always a concrete data structure. And it looks like this. So a list is always, a list is one of the following, right? It is either what's called the empty list, right? So there's only one empty list, as you might imagine. Or it is what's called a cons list, consisting of the first element and the rest list. Okay, that makes sense. So this is, no matter what functional language you're looking at, they always use this data definition, and it's mainly then a question of what is the notation for these things. Okay. So in Haskell, the way the empty list is written like this. So open bracket, close bracket, and cons is written like this, like a colon, right? So here's another thing to know about Haskell. So Haskell allows you to use names that consist only of special characters. And when you have a name that only consists of special characters, it is an infix operator that goes between the arguments rather than in front. Okay? So, which means that, and this, of course, if you think about, there's plus, and then there's times, and so on. These are all, in Haskell, those are not super special syntax, but they are just the names of infix functions in the language, right? And so is the case, such is the case here too, so this also goes infix. So how do you do a list? So let's say we've got a one-element list with the number 5 in it. That would be list 1 equals to 5. Cons the empty list, right? And you can see here the notation at the type level is that you put brackets around a type, and what you mean is the type of the lists of the of integers in this case. Okay, so you've got this, right? You've got list 2. So let's say we've got a 2-element list with 8 and the number 5. Then we would write it like this: 8 colon 5 colon. So you do one cons list. So you do one cons per element of the list, and it's an asymmetric definition. Does that make sense? Okay. We could spend another half day programming with lists, so I'm just going to do a speed run through that. Right. However, there is a. So let's say we want a 3-element list that is like 3, 8, 5. Now notice we could write it like this: 3, 8, 5, like this. Now notice that this part here is the same as this part. You see that? Right? The latter part is the same, so we could reuse it. We could also write 3 cons list 2. That would be the same thing. Okay, and that's what I mentioned earlier about sort of functional data structures, in that you can't tell the difference between those two things, right? This would probably operationally occupy like separate pieces of memory, and this one, and this definition that we have here, shares the memory with list 2. I'm glossing over a lot of sort of operational details here, but you can do this safely in functional languages. Okay so far? Is that clear enough? So let's say we wanted to program with lists. Let's do a very simple function, list sum, that just takes a list of integers and gives us an integer, right? And just sums up the elements of the list. Now, we can use the same technique. I mean, how many equations do we need for this?
2.
Why 2?
It
is one of two things, right? We see up here there's 2 cases, and therefore we need 2 equations. That principle really holds throughout. So we can say list sum. Now the only question is how to write this. And remember, I told you here, well, I should have told you one more thing. If you could also write list 3 prime equals. There's syntactic sugar to write this by just putting your elements inside square brackets and putting comma between this. But this is just syntactic sugar for that form up here. Okay, the internal data structure is exactly the same. So now we would write these equations like this, right? List sum, the first case is the empty list, And the second case is we got to mention the constructor, and we got to mention what's before and after. And again, I would like to call this, let's first call it first and rest, so that we know how to deal with this, right? So this is what the two patterns would look like. So you can see that the pattern, just like the construction of the list with the pattern, the colon goes in the middle between the two attributes of the const list. Okay? Now, when you're in the IDE, right, it often helps. You can kind of go, you can hover over identifiers, and we'll tell you what the types are, right? So remember, it's asymmetric. A const list splits into the first element of type integer, and the rest, which is a list of integers, right? So it splits after that first element. So in this case, right, we can say, and here's something else, which is a larger design principle in, well, not just in functional programming, but it's pretty much specific to functional programming. You notice that the term list here, it occurs in its own definition, right? A list is one of the following, then it says it's a constant, right? And so this thing is as self-reference. And whenever we have self-references in our data, there needs to be a recursive call in the template for that function, okay? So here, here with rest is the self-reference. That needs a recursive call that we can just write down. So I don't know if you've, any of you, in my generation, lots of people were traumatized by recursion in their intro class because somebody did like the Fibonacci thing or something like that. But really, what's relevant is when there's a self-reference in the data, there's a recursive call in your function. And it's as simple as that, right? And now you can see that, and I mean, of course, generally you should, when you see this, right, you should probably use both first and rest on the right-hand side. So when you read this, you can say, well, somebody's asking for the sum of the list consisting of the first element like so and the rest of the list like so. And I have the first element here. That's what I have. And I put the recursive call. I put that there without thinking, right? I've got the recursive call here. And I've got the sum of the rest of the elements. Those two things I have. I have the first element, and I have the sum of the rest of the elements. How in the world could I turn this into the sum of all the elements in the list? I put a plus between, I add those two things, right? So, what goes here? What is the sum of the empty list? Huh? 0. Why is it 0? Does that even make sense? It's an empty list. You have nothing to add. Literally nothing to add. 0 is the neutral, and there's an algebraic mathematical concept that's there. Oh no, here's the category person. Go away. So, yeah, okay, well, I won't go too deep. Well, we'll see how deep we can get. Right now, I'm just going to gloss over that. Okay, list sum, okay, as it is. Okay, folks, I'm going to move really quickly, so you need to tell me when I need to slow down in this point. Okay, let's do one other function. I'm going to call that list map, and you've probably seen that in your language of choice, even in Java or something that exists. So the idea is we're going to add, we're going to apply a function to each element of a list and return the list of the results, right? And the definition of that would look like this, right? We need two equations, right? We've got that function f. The Haskell people would never write first and rest because they hate typing, remember, right? And they would typically write x and x's, right? If you saw Simon's talk this morning, you saw plenty of that in action, right? So ask Simon if he likes typing. He'll tell you. Okay, so we've got this. So, of course, when we apply a function to all the elements of the empty list, there's nothing to do, so we get the empty list back. And in the other case, again, we need a recursive call, right? That is the recursive call. We probably need to do something with x. And so now we've already applied f to the rest of the list. We've got that first element, x. We still need to apply f to x. And I'm going to put, even if the Haskell people will hate me for it, I'll put parentheses around this like this. Does that make sense? So we apply f to the first element of the list. We apply f to the rest of the list. And then we put we cons those two things together. And that gives us a list of all the results of function application, right? Now, you can see here, and this is completely non-deterministic. Somebody's going to explain to me why it is like this, but it should. So here's the type signature for this. And you notice that the type signature contains these things called type variables. And you recognize that they're type variables because they're lowercase, unlike the types that we have defined ourselves, right? And the fixed types, right? And a type variable just means you can call this function, you can plug in anything that you like, right? And we had a conversation over the break over this, right? You can plug in anything that you like. I criticize that the Haskell people often only give one-letter names to things. Here it is appropriate because you know nothing about the A or the B other than the fact that they could be different, right? So there's no point to give them elaborate names like, I don't know, element 1 or element 2, right? Your number 7 doesn't care if it's an element of a list or not. Does that make sense? Okay. So far, so good? Okay, now, I'm looking at this list and seeing how far we can get down this list. Now imagine we wanted to write a very simple function that finds an element in a list, right? That gives us its index. Where is it in the list, right? Our snake has escaped and we want to find it again. So we want a function called listIndex. The idea is that it takes an A, a list of A's, and will give us an integer. Does that make sense? Okay. Yeah. Yeah, shut up. So how many equations? How many equations? Huh? No, how many? There's lists. How many cases do lists have? They still have only 2, right? So we go list index of some element, and we've got the empty list, and we've got x's like so. So what comes out here? C++ programmers. What comes out here? -1, right? No? Huh? Huh? But 0 would mean it's the first element of the list, right?
Yes, but the list is empty. So you index at 0 and then you get the...
Okay, that sounds even scarier. Yeah, do you understand that there's a problem here in that the type signature suggests that we always get an index, but we don't, right? Because the element might not be in the list. Understood? Okay. So we somehow, as I said, we could work around this, right? We could, I could write undefined here, right? Then our program would just run into an exception. But this is really a situation, Simon would say, it's just a failure. It's something that's completely normal. But it's something that definitely can happen as part of normal execution. And if we return like a negative number or something like that, that would be possible and would allow us to do many things. But the problem is, we would not know, the type checker would not help us if our program forgets to check for that -1, right? And that's a common error. In my days, I was programming C in the 80s, and all those functions return -1. If you forget to check them, the program just keeps on running. It indexes negatively into your array, and funky things happen, right? So we really, in Haskell, what we try to do is we try to make illegal states unrepresentable in the sense that we try to make our types precise as to what the function is trying to do, right? And therefore, we want to kind of say that this function, it might produce an integer or not, okay? And to that end, we could define a data type. I'm going to call that optional. Of course, that data type is built in under a different name, but you said optional, right? So now I'm getting to your point, right? And we could go like, let's call one thing null, right? And let's call the other thing result. And that contains an A. You can see that I can also, up here, we saw that you can have lists of like unknown things or things with a type variable in there. We can also define our own data types with type variables with kind of a notation that's very similar to defining functions, right? And that is no accident, right? So optional of A an optional with an A inside is either null or a result, and here is the type of the attributes that's there. Okay, so now we know, so now we can fix up that return type here, and we can say optional integer. Okay? So far, so good? Okay. Now, yeah, we'll see how this goes. Well, I'm leaving a lot of things out. Well, so now it says, now we can just return null here. And, this will, the effect of this is that anybody calling list index will have to consider both of the cases in the data type. Otherwise, the compiler will complain. Now, what goes here? Without thinking. What do we need? It's a function that operates on a list. In the case of the cons, what do we always need to put there? We need a recursive call somewhere, right? So we might as well write it down so we've got it for later, right? We also should probably do something with element, right? And with x, right? X. Well, namely, wouldn't it be nice if x was the element that we're looking for, right? Then we'd be done. That'd be great, right? So let's compare those two things. And, this will yield a bool, as we can imagine. What's the destiny of a bool in this world? Huh? To be, yeah. The bool just wants to go like downstream and is yearning for the moment when it hits an if that can differentiate between the true and the false, right? And we haven't done an if yet, but there's an if in Haskell. Looks like this, if, and then we do then something and else something else, and we'll keep that, okay? So if that element is the first one, right? What should come out here? What is the current index? If this means that it's the first element is the one that we're looking for, right? And well, you could ask we're going to do this zero based. So it's result. Yeah, we can. Yeah. Go say hello to the 70s, the 1970s. So we're just going to say that in this case it's 0. Does that make sense? Right? And of course, if we just write 0 here, it's going to complain really hard because it says, well, you need, what is it? So error messages are not always super great, but the error message is essentially that we need to have an optional and we don't, right? And therefore, we need to put this here. Okay? It's a little verbose, but it really forces you to use, APIs should be hard to misuse, and that makes an API hard to misuse because you're making different states explicit. Okay, so far? So now, in the other case, it's not the first element. Then we can do this recursive call. And the recursive call tells us if the element is in the rest of the list, in X's. That return value will again be of type optional integer. Optional integer has two cases, remember? Right? And remember at the very beginning I told you how to distinguish between the two different cases in the middle of a function using the case construct. Okay? So we're going to call case here, we're going to use case here, and that might be null something, or it might be result of some index. Okay? So in this case, with null, well, in this case, that means, well, the element is also not in the rest of the list. It wasn't the first element. It's also not in the rest of the list. Therefore, we can just return null here. And in the other case, well, it's in the rest of the list. It has index such and such in the rest of the list. But we're really considering a list that has one element in front. So we need to adjust that index. Is that clear to people? Maybe a little bit subtle. So we need to, again, so good, we found it, but the index will be one higher than this. Okay, moving fast. See a couple of puzzled faces. And I hear people typing, so maybe I should give it that moment. So, great, right? Let's try it. Well, there's a red squiggle. You see that? Right? What does that red squiggle say? It says no instance for EQA arising from a use of possible. That is gobbledygook, right? What does that mean, right? But it says possible fix add EQ to the context of the type signature. So I happen to know what that means, so I'm going to do it. So it says add EQA to the do this, and then the squiggle goes away. Now, folks, this is something new, right? We haven't seen that before because it's a double arrow. What does this mean? This EQA is what's called a constraint. And the reason for that is that in order for this function to work, it's got to be possible to compare the element that we're looking for with the elements of the list. And this equality operation makes sense for some types, but not all, right? So if you've been programming Java for a while, you know that every reference type has an equals method, but you don't always know how to implement it, right? Or sometimes it's not clear how to implement it. Specifically, so the classic case, maybe a little bit theoretical, is if you had a function type, right? How do you compare two functions? You've got to call it with all the inputs and see if the same output comes out. That is undecidable. Does that make sense? So some types, their values are comparable, you can compare them for equality, and some types you cannot do this. And Haskell distinguishes those two different kinds. Right? It says, okay, you can call this function with any type as long as it fulfills this constraint and that the values of that type are comparable. And then that gets introduced to this function. So if we look at the documentation for this, we can see that the EQA double arrow is in the type signature for the double equals, for the equality comparison function. Does that make sense? Okay. Okay, so far? Okay, let's try it out. List index, 3 in, 0, oops, what's that? 4, 3, 2, 5. I'm sorry?
2, 5 at the end.
Yeah, that is a great error message, right? There is, we got it. So here, no instance, we're getting closer to what this means now, right? No instance for show optional integer. Remember, that means that this magic line is missing. Okay, and let's try this again, and that gives us the correct result. Okay, great. Okay, so far, as just the general issue that you might sometimes want to constrain your type variables. Any type variables, but it has to do this. It has to support equality. Now, let's just for fun look for the snake, right? Here it is, right? And there it says no instance for EQ pet. In other words, right, pets are not comparable. Okay, it's a type we defined ourselves. We didn't do anything to make them comparable, so they are not.
Can you just do deriving EQ?
So we're getting a little bit ahead of ourselves. So now we need to look at, well, what is this thing EQ, right? And you can ask the REPL like this, info EQ. And it says it is a so-called class. And there's all kinds of stuff that we don't want to see. So this is so somewhere in the Haskell standard library, there's this definition here. I've abbreviated a little bit. And now, unfortunately, they use this name class and think, so this is what's called a type class. And if you're coming from object-oriented programming, you should think of it not as as something analogous to a class, but analogous to an interface. Okay, and it was just this year that I learned why they called it class, to annoy the OO people. Phil Wadler told me, he's on record. Literally, you can. We did a Haskell interlude episode with Phil Wadler. He says that somewhere. So we picked that to annoy the OO people. Okay. So what we can do is we can define what's called type classes that are interfaces, and of course, and then we can say, well, this type implements that interface. Other types do not implement that interface. Does that make sense? Okay. So and of course, we haven't done anything to implement that interface for dogs. Now, in order to implement it, so an implementation of an interface is called an instance in Haskell terminology. And if we wanted to find that snake, we have to go back and have to provide an implementation of the EQ type class for pets. Okay? So we're going to do that. So I'm going to go back to that type here. I'm going to write, well, it complained. It said no instance for EQ pet. So I'm going to say, well, here is an instance for EQ pet. And if I write these words, it says, well, you got to implement either equals equals or this is not equals. So the other way around. You could also implement that. We're just going to implement equals equals. And you will notice that equals equals consists of special characters. So people expect it to be written, so the compiler expects it to be written infix, except when there's parentheses around. So that's what we're going to do. So how many cases? How many equations? Ha! Gotcha. Unawares. But the data type is right there. How many equations? Well, in principle, we need 9 because so equals equals has to have type pet bool. We can't actually write that in standard Haskell, so I'm just going to leave that as a comment, right? And so because there's 2 pets going in principle, you need 9, right? So you need like dog. You need, well, and you kind of go, well, okay, that's true. 2 cats are also the same, and 2 snakes are the same. And everything else is not the same. Do we agree? Right? And so we can just we can summarize the other 5 equations by just saying false, the other 6 equations by just writing false here.
And then can you do the first 3 parametric?
No.
Like
no. Huh?
Something like
No, you can, let's try that. Good point. The questions people ask, interesting. So let's try. It gives an angry squiggle, and it says conflicting definitions for A, because each variable can only occur once. There's deeper algorithmic reasons why it is that way. Let's leave it at that, right? So unfortunately, can't do this. So you've got to write. So, but you can see that, again, this is getting tedious. It's getting to be a lot of typing. The Haskell people don't like typing. So this is why you could also write, you could comment this out, and or maybe, wait, let's try this out first. Let me split this. Let's go to the bottom. Let's see. We wanted to find the snake in here, right? And now it works, right? So first of all, now that we've got that implementation, now it works. But again, the Haskell people don't like all this typing, and this is standard, right? You say, well, I want the equal things to be, return true from that function, and therefore, for some specially treated type class in Haskell, you get automatic implementations by deriving EQ. Okay? So and now it is finally time to explain what that show thing is, right? We can ask, in the end, what is show? And it says, oh, it's a type class. Okay? Again, I'm going to cut some stuff that we really don't want to look at right now. So it's a type class, right? And again, it's similar to, and it has, these things are called method. It has a method that returns a string for each value of that type. Does that make sense? Okay, so far? So it's similar to the toString method in Java, right? But again, the difference is toString don't always have a reasonable definition, and therefore Haskell distinguishes between types that implement this and types that do not. Okay, so far? All with me? Okay, so we're getting on the end run, a half an hour of deep focus. Okay, yes?
Questions on the type class. Could
Yeah.
also write a type class describing functions that return the type. Like there is a function that takes the input.
Yeah, absolutely. You can do that. Yeah. And that's
That's a very annoying thing the old people always get wrong.
Yeah. Yeah, that is exactly what gets fixed. Okay, so far so good. Moving quickly. Okay, so type class is the central innovation of Haskell when it came out, right? Is really something, and it's an incredibly powerful mechanism that can do a lot of things, right? Now, let's go. Well, maybe you thought here, this feels. Well, no, it doesn't.
How do we derive show for the optional type if we don't constrain A?
Well, implicitly this means that the optional type is going to implement show if A also implements show, right? So you can implement sort of causality in the definitions of both the type class and the instances, right? We're not going to get into that because I'm trying to make progress on this list here. So we'll see where that goes. Okay. So we've seen list map, right? We've seen the optional type. Now we could define something like this. I'm going to call this optional map. And it has a type like this. And it's got how many equations? 2, right? Because optional has 2 cases, right? So we've got optional map f of null and optional map of result of A, right? And the way we can do this is, well, for null, we've got to return another optional, so this can only result in null, and this can only result in result of f of A. Does that make sense, right? We need to return an optional b, and the only way to get a b is to call this function. For that, we need an a, and we've got an a, so we call it. Does that make sense? Do you see why I called this optional map? Can you all go like, or Okay? So do you see the similarity between the type signatures up there and up there, right? It would be even clearer if they didn't have this silly brackets notation and just wrote the word list there, right? Then it would really be obvious.
You can write the brackets in prefix.
Really?
Yes.
Seriously? So I could do this? Oh, no.
Without parentheses.
Even without parentheses? Okay, good. Okay, good. Very impressive, thank you. Okay, I'll use that next time. Okay, do we see this? Right? So there's this function. So we've got a type that has a type parameter, like the lists do or the optional type does, right? And then obviously for at least 2 of them, we can define this map-like operation that applies a function to that, to whatever it is that comes out or is of that type, that is the type parameter, right? And now, so the EQ type class, right, it defines what is common to all the types that support equality. The show type class summarizes what's common to all the types that support printing. And the same way we could think about doing a type class that summarizes what's the same between those 2 things, right? And that type class is built into Haskell, and it's called functor. Of course, that is a concept vaguely imported from category theory, right? But it's, but at least the inspiration is from there. Let's put it like this, right? And so here's the built-in type class function. It contains a function called fmap, and we can hopefully see how this matches, right? This matches and this matches. See this, right? So all we have to do is we have to, the type class is over at f, right? And for f, we just have to plug in the word optional here, okay? And so we can just say, well, we can say instance, right, functor of optional, where fmap is the same thing as optional map, and that at least type checks, so that's the way to do it, okay? What is it good for? Well, okay, so first of all, just to show you that we're making progress, you might have seen that is this word here, right? So we're getting closer. what can we do with that? Well, look down here. Here's this function. Here's this thing where it says, well, if it's null, it's null. If it's result, do something with what's inside the result. Add 1 to that, right? And now look at the definition of optional map. It says, well, null maps to null, and result maps to result of doing something to what's inside there. So maybe we could try applying fmap down there, making the code maybe a little bit nicer. So, and maybe you even thought, well, this looks kind of clunky, right? And so we could go, so we have that recursive call, XS, and what we do is we do fmap, and we now need, well, let's do index plus 1. Let's do an inc function, and we do fmap inc of this thing. Does that make sense? Okay, and we'll find out that it works exactly the same way. So this is just a simple pattern that we see repeatedly, and therefore it makes sense to define that as a type class, because there's a whole bunch of types that have a type parameter where it makes sense to define a map-like function and turn them into a functor. Okay so far? Right? Now, we've got a half hour. Let's see what we can do with that. Now let's switch gears a little bit. So we defined that optional type to characterize things where either a result might come out or not, right? Where maybe it could also characterize, something, an error occurred of some sort, right? Something just didn't work out, and therefore we're just going to return the null thing, and otherwise we're going to return the result thing. And we can use that to tackle a common problem in software, which is called validation, right? When does that occur, right? You're writing some sort of web internet-facing service, some request comes in with a bunch of JSON or a bunch of XML, and really that XML is supposed to get turned into data types, into values of data types that you have defined in your program. But of course, that JSON, it might be wrong, right? It might not occur, it might not conform to the schema that you have set. So before you turn it into data types, you should really validate it and make sure that it's correct before you turn it into Haskell data. Okay. So validation. You can do that one of two ways, right? Either you could just turn it into Haskell data and then look if the data is correct, right? Or you could validate it before you turn it into data, right? And I don't know if you've ever worked with validation frameworks in Java. They tend to use the first approach. Right? So you first create your Java object, and then you validate it. And that, right? And this is, have you seen that movie Alien? Right? Where they go are we going to let the alien, we want to examine it. Are we going to let it through the airlock? And then they go, let's first let it through the airlock and then examine it. And that is Java, right? Essentially, sorry. So we probably shouldn't do that, right? So the way to do it is let's say we want, I think I always use an example from one of the Java libraries, which is about cars. And so the idea is as follows. So you might have a data type car, and I hope I remember this correctly. And it's got some seats, right? And you could naively write, the seats is going to be an integer, and the license plate is going to be a string. Right? That would be a naive way of doing it. Okay? Yeah. Right. Now, unfortunately, the number of seats, it can't just be any integer, right? It should probably be, between, 1 and, 8, maybe, to make sense, right? And the license plate, let's say, should not be empty. Or at least 2 characters. Okay? Does that make sense? So I can write that as a comment, right? But the problem is there's nothing here that, if I create an invalid object, I'm not going to see that it's invalid at the type level. That's just like the -1 for the index in that indexing function that we saw earlier. Does that make sense? Right? And now remember that we cited this principle, make illegal states unrepresentable earlier. formulated by the CTO of Jane Street, Ron Minsky, who said, well, make your types such that you really are sure, that you really are sure that they contain the values that you expect. Okay? So, so what he's going to argue is don't just put integer here, yeah? Make a new type called seats, okay? And, right, and we're going to just make a new data type here that says data seats, mix seats, and we're going to plug the integer in here, okay? Does that make sense so far? Right? And now what we do is, of course, we don't want people to call that constructor here because they could call it with -1. Instead, we're going to provide a function, let's call it make seats, right? And we have some number n, and we say, well, if n is greater than 1 and n is less or equal than 8, then we use that optional type that we've defined, right? And then we say, well, in that case, we're going to say result mux seats n, and else we're going to return null, right? And so this turns an integer into a seats object, but only if the seats is correct. Does that make sense? Okay. And then the Haskell module system has a way of allowing us to hide this constructor and only exporting this so that people have to go through this function if they want to create a seats value. Right? Similarly, we could go data license plate mc license plate of string and call it like this. Now, okay, and similarly, yeah, let's first do that. Make license plate s and says if length of s greater or equal than 2, then result of mc license plate else null. Same thing here. And, well, you can see that a string in Haskell is just a list of characters. That is slightly quaint. Now, somebody asked about this earlier. Now, this, effectively, this type here is just a wrapper around string, right? You see this? Right? So you kind of think, well, okay, I mean, good for type safety, but it's going to carry runtime overhead, right? If I make in Java or in C++, well, in Java, definitely, right? If I put a class around this or a record around this, there's one level of indirection involved, and it's going to cause some memory overhead here. Therefore, in this special case where you have a type that's just a wrapper around another type, you can replace the word data by the word new type. And somebody asked about this earlier. And so it's the same thing. You can program it in exactly the same way. But the new type means that there will be no runtime overhead from this, right? It's only distinguished at the type level. There's some other funkiness attached to it at sort of the higher levels of Haskell, but so for now, we're just going to do it like this and treat it as the same thing as if we had written data in this, right? Okay, so far? So far? All with me? Okay.
That brings a runtime overhead.
So if I write new type, it doesn't have a runtime overhead.
If you write data, it does.
If you have data, it might. Let's put it like this, right? So new type really says, it really, the compiler must not create runtime overhead for this. Now, we could write, of course, usually what we want is we want then a function make car that corresponds to the old make car, where we can go, well, here's an integer, here's a string, and then out comes an optional of a car, right? And that only gives us a car if the integer is a valid number of seats and the string is a valid license plate. Okay, get this? So we've got the n, we've got the s, right? And now we could, of course, go like, okay, we got to call make seats of n, and we've got make license plate of s, and both of those are going to return optionals, right? Okay, so we got to go case. Right? We got it. Well, yeah, maybe. So, we could do this, right? And then we could go null, then we return null. result, seats, okay, cool. Then we could go, in this case, we could go make license plate S of null, result, result. And then finally, we could go mccar seats. What am I doing wrong? Of course, result around here. Okay, so we've almost made it. Okay, so far so good. And now imagine it's 3, 4, 5, 6 attributes in this, right? We've got complicated data structure. Nobody wants to write this. Case, right? This is why the Java programmers don't do it this way. Does that make sense? But you also see that the pattern here is very similar to the fmap pattern, right? Null goes to null, result goes something to the result. But what we need really is we need an fmap 2, right? For 2 things to go in. Does everybody see that? Right? So we need right? Does that make sense? So we could do that, of course. I mean, so we could abstract out this nested case, the nested case here for the 2. But of course, then somebody's going to need it for 3, for 4, for 5, for 6, for 7, for 8, for 9, for 10, and so on. And every time it gets longer. And you can't really nicely reuse the ones before that. So that sucks. Okay? Understood? So we could do it, but super annoying. And now in comes something called the applicative functor, right? Out of nowhere, right? So what is that? What is an applicative? We could ask, well, first let's ask, what is an applicative functor? And in Haskell, well, it's called just applicative, and we can see it is a type class. And it's got, well, this means that an applicative functor needs to be a functor already. We know what a functor is. And then it has to have 2 methods. One of them is called, so you have some type constructor here. You need a function pure that goes from a to f of a. So in our case, imagine it says optional. We need one that goes from a to optional of a. And then we got this funky function here, right? And that has a name consisting of special characters that the Haskell people all, I think most of them, like look around, like 14-year-old teenagers with zits. It's the TIE fighter. Okay? Okay, so this is called the TIE fighter. It's a funky function. We don't, who knows what it is, right? Okay?
The starship.
The starship?
Yeah, because it has the story that it looks a bit like an UFO.
Yeah, well, watch Star Wars, right? Yeah, go back to when you were 14. Okay, so far so good? Okay, so we don't know what this is, but we could try to implement it. Okay, so instance. So good thing is we've done the functor already. We're going to do an applicative of optional, and pure. Well, pure just turns an A into an optional of A, right? And this is the job that's, so if we got pure of A, we can just do result A, right? Stick it into a result and that will work. So far so good? Okay, now the funky TIE fighter thing, once, how many equations does it have? So it goes from optional of A to B to optional of, and then an optional of A, and out comes an optional of B. How many cases? How many cases does optional have? Come on, guys. Folks, we've got, 2, and we've got 2 optionals, therefore 4 equations, right? We're almost done. Okay, so the TIE fighter goes, well, so we've got null, we've got null optional of, not optional, result of A, we've got result of f of A, I'm just going to call this f, and null, and finally result of f, result of A. And we don't know what it's supposed to be, right? So, I mean, I've not shown you documentation or anything like this, but we know since an optional of B comes out, we know we need to come up with an optional of B, right? And for optional of b, there's two possibilities with which we could do it. We could either return null, or we could turn result. But if we're going to return result, we need to return a b. Understood? So if we don't have a b, we know we can only return null. Do we have a b here? No, we don't. So we have to write null. Do we have a b here? We've got this is of type A, but that's all we have. That's the wrong type. We need a b, so we can't do that here either. And in the next case, do we have a b? No, we've got a function that goes from A to B, so we would have a b if we had an A, but we don't.
What if A is a null? What if you have a function that takes null?
Huh?
Null is not a type.
Yeah, null is not a type. It's just a case in the optional type. Okay? So it would be really sad if this were also null, right? That would be super sad. So let's see if we can't make this a result. So we need a b. So fortunately, we have a function that turns, let's see if that still works. F turns an A into a b, and we have an A, so we can just call f of A. And what is it called? There's still none. Now it goes away. Okay, that's the definition. Okay, so far? Okay. So that is the type fighter. Okay. And now, so what we wanted was, we said, well, we really would have liked a function like fmap2 that goes from A to B. So we've got a function that is binary. We've got an optional of A, an optional of B, and then we got an optional of C, right? And so the idea is, if indeed we have an A and a B, we'll get a C, and otherwise we'll get a result C, and otherwise we'll get null. Okay, that's what we wanted. Remember? Okay. So, and we could have written it with nested cases, which is annoying, but we could now, so we've got this funky function f, and we've got this OA, and we've got this, or opt, let's call it opt A, and we've got the opt B. And now we could, so, well, the solution is actually the type fighter operator here. So how do we cram this thing? How do we get this to display at the same time? I'm going to move that down here. So, okay. Okay, so we kind of need to, what the Haskell people sometimes call type Tetris. So we somehow, so I promised you that the TIE fighter would be kind of the salvation here. So we've got the function f, right? So f has, yeah?
The strategy might be more clear if you make the parentheses around B to C explicit.
Yeah, let me do that. Good point. Yeah, remember, this associates from the right.
Maybe also around
okay, so we need so in order to apply the TIE fighter, we need an optional of A to B. So we need a function inside an optional value. So far, so good. Can you see this? So this is the last. You know, if you've got 5 brain cells, this is the place to expend them, right? So we can. So this type actually matches that one up there. Do you see that? Because in Haskell, all functions are unary, right? So this thing just means, so this thing down here just means it's got to be an optional of some function. Doesn't matter which, you know, as long as it's a function, it fits in here. The only thing is we need to get it inside the optional. Is that clear to people, right? You know, we've got this function pure. It puts something inside the optional. You see that, right? So we could try this. We could say pure of f. So that gets us inside the optional. Then we could try to imply the TIE fighter. And then this thing here, we need an optional A. So we need an optional of the thing that goes into the function. So we need an optional of A. Do we have an optional of A? We do. And now it's still, so now we need, so now the TIE fighter is going to get us an optional of, well, what is called B, and it's called, up there it's B to C. So we could use the TIE fighter again. Does that make sense? Right? So this thing here, if I, do I see this here? Not really. Yeah, no, I don't see it well with this thing. So, let's see if I see it here. Okay, this, what I've written so far, okay, I can ask the Haskell compiler, what type does it have? It has the type optional of B to C. Can you all note that you see this? Right? It has type B, it has type optional of B to C. And that means I can apply the TIE fighter again as long as I've got something of type optional of B, which I do. Okay? So I could do X of opt B, TIE fighter, yeah, and then type checks. So in other ways, I can now remove the let here and write it like this. Okay, yeah?
Could you get the same result if you do, instead of the first pure F TIE fighter of the, if you do F map of F?
Yes. Yeah, let's that one settle in, okay? So this means I get the binary F map I just get by repeatedly applying the TIE fighter, right? And this goes up to any number. And I don't know who asked what is the applicative functor. That is essentially what the applicative functor gives you. It gives you n-array map or n-array F map, right? And here's the classic application is to use it for something like validation. We could also use it really nicely. I mean, for reasons of time, I haven't done that yet. I haven't done that here. But it gets even nicer if you also want to return error messages when something goes wrong with the validation and really make sure that everything that everything that's wrong also gets reported, right? So this is a pattern, a notational pattern that you see in Haskell code. When you see the TIE fighter, you got to think n-array. So you got to think applicative functor, and then you have to think applicative functor means n-array F map. Okay. Now, as you pointed out, this is not the only way to get this to type check, right? The other way to get something working is you could remember that the, where was it? The functor type class, where is it? Ooh, here is it, right? The functor type class is kind of similar to the TIE fighter. So fmap is kind of similar to the TIE fighter, but it doesn't require an F around this, right? And so we could also, for the first one, right, instead of doing this pure thing, and if you're tuning out at this point, don't worry about it. This is just to make the type, because the Haskell people, you remember, they hate typing, so we're going to make it even shorter. F opta op B, and you could also do fmap F of opt B, and then just do of opt A, opt A, and then do opt B, and that also type checks. Okay, I mean, remembering that, right, this it associates like this. Okay? Now, the Haskell people looked at this and thought, well, this is kind of nice, but could we add more special characters to this? Right? And less typing, right? And so they figured, well, so they figured, well, maybe if we could make fmap be an infix operator. So actually, in Haskell, somewhere, somebody thought it would be a really cool idea if we did this. So this is exactly the same as fmap, right? And then you could write this f opta opt b equals f, and then you do this, opt a. So the first one is fmap, and all the other ones that follow are TIE fighters. Okay, and that also type checks. What does it have to complain about now? Oh, it's redundant. Yeah, it's redundant now. Okay, so this is, and so when you see this pattern here in Haskell code, TIE fighter, TIE fighter, TIE fighter, TIE fighter, that is just n-ary map, right? It's just apply a function inside something that's a type constructor, and that's often in contexts where you are either doing something validation or where you're doing something that sort of goes parallel. And now, let's see what we've covered. So I feel we've covered data modeling. We've covered make illegal states unrepresentable with this sort of very lightweight and very simple validation code. We've covered applicative functors. We have not covered programs that do stuff. Oh, we've got 4 minutes. And we now have not covered theorem proving, and we haven't covered quick check and effect systems. Let me tell you what this is about. I mean, I can hang out here a little bit longer if you like. But where's this going? The thing is, so in order to write programs that do stuff, we use something in Haskell. Well, we do it as we do everything. Instead, I mean, we can't write programs that do stuff, right? Because the language is purely functional. What we're instead going to do is we're going to describe what we want done as a data object. Okay? And that thing, and that has to be structured in certain ways, and the way to structure it is with something called a monad. Now, a monad is a slight extension of the applicative functor. So we've gone functor, applicative functor, and then you add another little feature, and then you have a monad, and then you can write programs that do stuff. So hopefully that's not such a huge step from what we have here. And then Haskell offers special syntax to deal with that. And then this is also usually what you will do is you will think of monads as defining effects, right? So that would be the next step up. So my time is up. Questions? Yeah.
So just to be clear, applicative functor is just the type of functor that has pure and the TIE fighter.
Yeah. So, I mean, let me say a word of warning. Maybe not with applicative functors, but with monads, right? There's a cottage industry of monad tutorials which try to work in terms of metaphors, right? They will say, I don't know, let's see. A monad is, well, there's always this T-shirt that says it's a monoid, and the functor, yeah, well, very helpful, thank you. But then it says it's a spacesuit or it's a burrito. I understand, there's this. I understand the tendency to explain things in terms of metaphors because that's the way, the human brain sort of appreciates metaphors. But the thing is, these things, functors and applicatives and monads, they're abstract concepts, right? They defy metaphors, which is what their power comes from, right? And so I recommend when you play with these things, don't read these tutorials that try to explain, it's a burrito or something like that. Rather, program with these constructs. And your understanding will come from usage and not the other way around. Right? And give your brain a little time with these things. This has been a wild ride, hopefully. Well, maybe not hopefully, but it has been a wild ride, right? We've been doing things extremely quickly. But for these abstractions, the human brain needs a little time. So don't sit in a corner here at ZuriHac and stare at the monads our burrito tutorial and go like, I'm not going to get up from here until I've felt Zen-like enlightenment, but just do some stuff with it.
How far can you go with just monads? It feels like it's just, for real programs, it's just another step, but you need something bigger or more complex.
No. So, is it okay to do a few minutes longer for questions and so on, right? And so if you need to leave, you leave. I'm here anyway. So when you write larger programs in Haskell in general, right? The way to do it is to write so generally sort of functional programming culture means you do this sort of bottom up. So you do domain modeling. Domain modeling and functional programming means modeling in terms of data, right? You model the things in your domain as data. And we've seen sort of things, right? We've seen our, our pets and our animals and our whatever list indices and our cars and so on, right? These are all data. These are all data. Now, and this lets you define large parts of your domain logic as just functions and data types. And this is what you should be doing for as long as possible. And you'll find that you can push this very, very far. So if you imagine your program as a ball, right, you kind of go work from the inside to the outside, and as long as possible, you write functions and you write data types. At some point, you will find that you will need to orchestrate what you're doing in sort of processes that have some sequentiality or that interact with the outside world. So here is maybe, here at the edges, there's external systems, there's your, you want it like databases, your database is here, and so on, right? Now, the way to do this in Haskell is you represent your process also as data. This is what monads are, right? What monadic values are just data objects that describe a process that does something, right? These tend to live here at the edges, and then at the outer rim where you do the actual communication, where you need state, right? Your database has state, right? There lives a special evil monad called the I/O monad, right? And the I/O monad contains all the sins of the world, right? It contains exceptions and I/O and databases and concurrency and immutable variables and all kinds of evil stuff, right? And you will want to keep, so this is something that you will only want to do as a last resort. Generally, your monads should describe your processes, not like, I'm going to write to this file. They should be in your domain, not in your sort of technical stuff that you're doing. But that's it, right? I mean, sure, so essentially, when you do this, right, here in the center for the domain logic, we haven't done this now as part of this, right? You will want to look at some algebraic structure in terms of semigroups and monoids. So somebody said, remember that list sum function where somebody said neutral element? That belongs to a concept called a monoid. It's pretty simple, but we haven't done it today, right? These are two type classes also that are built into Haskell. And here we've got this hierarchy or this little tower where we say functor, applicative functor. So a monoid is a semigroup with an extra feature. An applicative functor is a functor with an extra feature. And a monad is an applicative functor with an extra feature. So you've got these 5 concepts, right? And those will get you all the way, right? I mean, there's more. If you go to the category theory track, then they'll tell you about more useful concepts, but this is what covers your needs.
And I've never really written a program for that, but there's always this composition issue with monads, right? That you have different monads that get them together.
This is why, so, I mean, there's a more involved question here, right? In that, historically, right, when monads came up, we were mostly defined monads for technical things, like for file I/O, for network I/O, for writing to the database, and for things like this, right? So these all in Haskell live in the I/O monad, period, right? You can try to subdivide that more with an effects library. You can do that, right? But I'd like to argue that it doesn't buy you all that much if you keep this I/O layer thin. When you define your own monads, right, these should not be, there's a good Bob talk by Andres Bleu, by the way, on this. When you define your own monads, these should be in terms of your domain, not in terms of technical things like state or exceptions or whatever. They should be in terms of domain. And there you don't need composition all that much, right? So if you need composition, that's kind of the higher, the higher Zen enlightenment level of enlightenment. You'll get there, but I suggest that you first do this in a very simple manner. Define a data type for your monad. Do that in terms of your domain, and you'll get there. And the I/O monad, so you kind of give in. You say, okay, that's it now. And you keep that code here thin and disposable. And you can do that. In practice, you are able to do this, and that does away with a lot of sort of the deeper rationale for a lot of funky effects things, right? The effects things are good, but they tend to be overused at that stage. Right? If you're here, if you keep this simple, and you can keep this simple, then I wouldn't worry about it too much. Right? Yeah.
Two questions, one more practical, one a bit less practical.
Yeah.
Can you maybe show how this make car becomes now that you introduce the apply function?
Oh, okay, sure. We never did that, right? So now we can compose, right? So we can say make car ns is the same as mc car, and then we can say what is it called? Make seats, and so this is kind of what we intuitively would like to write, right? Right? So we apply this to the result. We reply mc. Is that it? Hopefully. Make. I'm sorry. Make. So like this, right? This is intuitively what we want to do. Is we want to apply mccar to the results of that. But because they're stuck in the optional type, we just sprinkle a couple of special characters in between, like so. And now you can even remove the parentheses, and the Haskell boys are really proud of that one, like that, right? That's it, right? This is the way to think of it, right? It's just function application with a little bit of syntax sugar on top, right? And
a second question would be, so we saw that we can implement this star, whatever operator, this apply, without using pure. So why did we have to introduce, why was that introduced in the applicative type class?
You don't need it here. I mean, pure is kind of a nullery fmap, right? Maybe that's a way to think about it. I mean, so it's just part of the applicative formalism. I don't think I have a good answer.
Was not introduced in monads, for example.
Yes. Yes, so it is part of applicative just because it's part of the sort of primitive, of the abstract notion of what applicative functors are. I mean, I told you this application, right? But there are other applications that require pure. This one doesn't. Right. Yeah, good point. It's not.
We talked about the derived mechanism.
Yeah.
I'm just wondering if this is like a compiler thing and there is a couple of magical type classes.
Yeah, there. Yeah.
So it's not extensible in the user space.
Well, I mean, the thing is, no, it's not directly extensible. I mean, the thing is, though, that type classes, I mean, I've shown you how to implement sort of type classes for types in the sense of, right, you've got nothing, and here's the implementation of the type class. But often you can implement type classes if you've got some other type classes, right? So, for example, with these semi-group and monoid things, if you've got two monoids, right, the tuple of monoids also forms a monoid, right? So, and that's a compound data, right, that you've got there. Yeah, so first of all, for your data types, if you construct them in this manner, then often you get automatically the type class instances that you need. You don't need deriving. And then there's a feature that says, well, if you've got a new type, and all it is it's a wrapper around something that's got type class implementations, then I'll just give you those automatically, right? But this thing where it will actually generate like code for the equals function or the show function or something like that, that is basically restricted to a few magic type functions that are built into that the compiler knows about. Somebody will correct me, but it's probably more. There's probably a more involved and very convoluted story behind this, but essentially, I think that's the truth. Okay. So I've got this. So what was it? There's a chillaxing area out there. So please all go like, if you've like managed to get keep up with anything, go like this, please. Congratulations. It's been very, very fast. I hope you got something out of this. I'll just hang out here if you have more questions. I'll hang out here if you want to know about monads and how to do stuff. We have the room, right? Yeah. I'll just be here. Yeah. So I'll just hang out here more if you've got more questions. But otherwise, thank you for being here. Thank you for asking questions. And thank you for just staying with it. Great work.
Thank you very much.